We are so excited to welcome you to the SPI, ESI, and North America Smart Energy Week virtual trade show. With nearly 200 participating exhibitors from across the renewable energy industry and 100 live education sessions, we are proud to bring you a robust, energy-filled 2 days of opportunity and access to the best of the industry. Take time and visit with all of our exhibitors who are available to live chat with you over the next 2 days. And make sure that you've created your My Show Planner account so that you can interact with all of our exhibitors. Every day, there will be a dedicated live chat time block from 2 to 5 p.m. Eastern so that you can chat with the exhibitors. And all of this is brought to you by EDF Renewables. Let's give them a virtual big round of applause for their support.
Now, we would like to recognize each of our sponsors for their support not only for SPI, ESI, and North America Smart Energy Week, but also their support to the industry. They truly contribute to the quality and success of this event. With that, our one and only highest sponsor at the megawatt level, SolarEdge. Also, be sure to check out and explore SolarEdge's interactive 360 virtual booth experience. You can easily access it from their virtual trade show booth, as well as here on the homepage of the virtual trade show. We'd also like to recognize our kilowatt level sponsors, Doosan GridTech, LG, EDF Renewables, Black & Veatch, and Jinko Solar. And for our watt sponsors, Baysfield, Eaton, Block Energy. Our premier sponsors, Enerbank USA, Nearmap, and Veritone. And for our supporting level sponsor, Solar Ranch Development Company.
We are lucky to have some of the best-in-class industry partners any organization could ask for. We'd like to give special recognition to the California Fuel Cell Partnership, the eMERGE Alliance, Forth, and Solar Energy International, whose continued partnership has ensured we provide industry-leading content across the entire renewable energy landscape. Our industry partners play a key role in the success of SPI, ESI, and North America Smart Energy Week, and support our efforts to bring renewable energy industry professionals together to open the conversation about what is impacting the industry, best practices, and more. Now, stay tuned and watch this short instructional video that will walk you through how to create your My Show Planner and successfully navigate our virtual trade show so that you can see exhibitor demonstrations, access collateral, and even live chat through the virtual business cards that have been added by each exhibitor.
Welcome to the virtual event My Planner. This tool has everything you'll need to make the most of your time searching and networking online. While exploring the online directory, you can save exhibitors, products, documents, contacts, webinars, and more. With a My Planner account, you can access exclusive content only available to My Planner users to make the most of your event experience. Creating an account is easy. Simply click the Create Your My Planner option and complete the registration form. Select Yes under the Connect with Exhibitors section to share your name and email with exhibitors you add to your planner. Select Create Your Free Account and you'll be all set to start exploring and saving resources. The online directory includes everything you'll need to explore the event. This intuitive layout allows you to access the search bar, quick links, and a couple of different ways to view your search results. The quick links allow you to quickly access important areas including new products, featured companies, webinars, and special offers. Click into the search box to see all available search options, including a broad keyword search, allowing you to explore a variety of content simultaneously. For example, when searching audio, you will see search results pulled from various content areas, such as exhibitors, product categories, show features, brands, and more. You can also toggle over to the Education menu option at the top of the page to use event-specific search criteria. Choose from two different options when viewing your search results. Option 1 is the grid view, which will present your results as tiles with additional information previewing the details page. The second option is the list view, which will display the same information but within a listed format. Click into the search results on either view to see additional details and options for adding this information to your My Planner. As you start to explore the directory, you'll notice a new notification in the top right corner of your screen. By clicking here, you will be taken into the MYS recommendation engine that will make recommendations based on event-specific activity. This tool uses AI technology to reveal what like-minded attendees are searching for to help you explore every avenue while attending the event. By clicking on the bell icon, you will see your own personal recommended results for exhibitors and education events based on your directory activity. You can click on these results to learn more, add to your My Planner, or dismiss them to make room for additional recommendations. The recommendation engine allows you to see your own personal list of can't-miss companies to start networking with. As you explore the directory, don't forget to save exhibitors, products, and other resources by clicking the plus sign icon. You can then access your saved items in the corresponding sections of your My Planner. Click the My Planner option in the navigation menu to go to your planner homepage. The homepage includes an easy-to-navigate layout. Simply scroll down or navigate to a specific area using the menu options at the top of the page. You can save scheduled events such as networking sessions, training, guest speakers, and more to your My Events calendar to keep track of your schedule. Within the Exhibitors section, you can see your saved exhibitors, mark who you have spoken with, and take notes all in one place. If you are interested in learning more about a new product featured on an exhibitor's listing, you can add them to your My Planner and they will be saved in your Product section. Save press releases, white papers, brochures, case studies, links, and other items uploaded by exhibitors in your Collateral section. Documents can also be downloaded and saved to your own personal device. Explore show specials to save special offers such as discounts and giveaways that have been posted by exhibitors. View virtual business cards and save them to your Contacts section. You can also reach out to these contacts via email through your My Planner account. Your Recommendations section will list your own personal recommended results based on your directory activity. It's that easy. My Planner has everything you need to maximize your virtual event and networking experience. The MYS chat is a way for attendees to connect with exhibitors in real time. My Show Planner users can easily engage with exhibitor contacts through the one-to-one chat function available through an exhibitor listing or through the new chat interface within the Planner dashboard. This feature is available to all My Show Planner users with just a few easy steps. Both attendees and exhibitors must first create a Planner account, verify their email, and enable the chat feature in their profile settings to send and receive messages. Using this tool is easy. Simply log into the planner and click the My Chat button. Here, attendees can view their saved contacts along with a full list of all contacts. Any exhibitor who has the green tag labeled Available is currently available for a live chat. To start a chat, attendees can simply click the chat button to the right of the contact's name. They can also start a conversation by clicking the chat button next to the online contact information on the exhibitor's details page. If a contact is not available for a live chat, attendees have the option to reach out by email directly. The contacts listed on the exhibitor details page are based on the information entered in the online contacts section of the exhibitor dashboard. Exhibitor contacts will see any messages they have received when they select the My Chat button. They can network with attendees and see their chat history indefinitely to revisit information when they follow up with leads. If attendees or exhibitors navigate to another part of the online directory, they will receive an alert at the top of the page when they have an unread message. They can click the banner to navigate back to the chat area or close to view unread messages at a later time.
Welcome to SPI, ESI, and North America Smart Energy Week, the largest event in North America for the renewable energy industry, including solar, storage, smart energy, wind, hydrogen, and fuel cells, geothermal, and EV infrastructure. Thank you for joining us from your home office. My name is Evelyn Butler. I'm the Senior Director of Codes and Standards at the Solar Energy Industries Association and your installer training track ambassador host for the next 2 days. My role is to help you navigate content and exhibitors as a solar and storage installer. I've had the pleasure of participating in many of the show tracks over the last several years, and I find that the technical training content is critically important to understanding the recent changes in codes and standards that have recently developed and will be required in the coming years. Code improvements, such as the California requirement for solar on all new low-rise residential, and the option for storage compliance is a great example. We've featured tracks and sessions on those topics in previous years and have similar sessions for you this year. Over the next 2 days, I recommend that you check out the following sessions to gain technical insights and connections. Tools and techniques for commissioning and maintenance of PV systems, the 2020 National Electrical Code PV and energy storage systems, residential energy storage systems, PV installation best practices, and the physics of solar cells and IV curves. These sessions will be played here on the Installer channel. The following exhibitors are innovating and leading the charge in the installer space. Please head over to the Virtual Expo Hall platform to engage with these exhibitors and learn more about their innovations, technologies, and products. Solar Energy International, or SEI, 17 terawatts, American Ground Screw, and NABCEP. I'm excited for this opportunity to learn and engage with you at the virtual show over the next 2 days. To stay up to date with the installer world, I can be reached at ebutler@sia.org.
Hello and welcome to this training on tools and techniques for the commissioning and maintenance of PV systems. My name is Kelly Larson. We at Solar Energy International realize that everyone is affected by the COVID-19 pandemic, and we have stepped up to offer more online training and some discounts for you. We are offering SPI attendees a special discount, 50% off on our online courses. You can see here we have several courses that range from the introductory PV 101 all the way up to our operations and maintenance class for more experienced technicians. We cover batteries and also have a technical sales class. So 50% off on each of these courses. We also have a package of safety courses we have put together that focus on PV specific topics for only $99. We also offer a battery safety class that is free to those in the U.S. and working in the solar industry or prospective solar energy workers. Find more details on our website at solarenergy.org. We also offer continuing education courses on demand. You don't have to wait for a new session to start. These cover different sort topics like the changes to the 2020 National Electric Code that are relevant to the solar industry, and basics of site analysis, and also tips, tools, and techniques of the solar industry. Solar Energy International classes are excellent, and it's an opportunity to join the more than 75,000 SEI alum. I've been working in the solar energy field since 1996 and teaching for Solar Energy International since 1999. I started my career working for Alternative Energy Engineering, which is now called AEE Solar. I designed and installed off-grid systems in California for about 20 years. Now I contract design and field services, mostly through Solar Energy International's Professional Services, which is a for-profit branch of Solar Energy International. Before we start, I'd like to say a little about safety measures we must take to stay safe while we work. Make sure you have the proper PPE for the work you may be doing at any site. Consult NFPA 70E and or a professional engineer as needed. As mandated by the NFPA 70E, when working on energized equipment within the arc flash boundary and the shock hazard boundary, arc rated clothing, and protective equipment must be worn. Do not perform the work if you are not a qualified person with the skills and knowledge necessary to recognize and avoid the hazards. The output characteristics of any given module or series string of modules are characterized by a performance curve called the IV curve. The graph of the green curve shows the relationship between current and voltage output. Voltage, or volts, represented by a letter V or E, is plotted against the horizontal x-axis, and current, or amps, represented as A or I, is plotted along the vertical y-axis. Manufacturers generate IV curves under standard test conditions, meaning 1,000 watts per square meter or radians, often referred to as one peak sun, and 25 degrees or 77 degrees Fahrenheit cell temperature. We're talking about the cell of the module. Standard test condition represents standard conditions for module performance, and it provides a consistent reference point to differentiate between IV curves of different modules. However, these conditions, bright sun and relatively low cell temperature, are not representative temperature and irradiance for typical field operating conditions. When PV modules are out in an operating array, the temperature of cells is often 20 to 30 degrees above ambient temperature, and the irradiance varies greatly throughout the day. Plus, the array is subject to shading, temperature, and the irradiance varies greatly throughout the day. Plus, the array is subject to shading, mismatch, and dirt buildup. Thus, an IV curve can be taken in the field may appear different than the manufacturer's curve. There are 5 different points in the IV curve: open circuit voltage, short circuit current, the maximum power point and its corresponding voltage, VMP, and current, IMP. Now, if you are new to this, you might think circuit, you think circle. Electricity needs a closed path or a circle to do work. An open circuit is like an open circle, so no current can flow and no work can be done. We measure this work in power or units of watts. Two of the points of the IV curve are present when the module is not operating. Open circuit voltage, or VOC, occurs when the module is not connected to anything. Our circle is open. Since the module wiring is not connected to anything, no current can flow, and as a result, VOC is read on the x-axis, the point where the current is 0, and the voltage is the highest. On the IV curve here, VOC is about 42 volts. Since there's no current, the module power at VOC is 0 watts. Remember, volts times amps equals watts. Again, that's just exactly what you'd expect from a system that's not operating. A short is when the electricity is going around in a circle unencumbered. With nothing in the way, the maximum current flows. Short circuit current, or known as ISC, is the max current that can be produced by the module under STC conditions. On the IV curve, ISC is read on the y-axis, and here it's about 8 amps. Because voltage is 0 on the y-axis, power output, as with VOC, is 0. Volts times amps equals watts. Again, you'd expect that from a system that is not operating. Now, the last 3 points are present when the system is in operation. There's voltage to push the energy around the circuit, and current is flowing. We know the power equation, volts or voltage, multiplied by amps or current in watts. So when there's voltage and current, there is watts. The system is in operation. The maximum power point is at the knee of the IV curve and represents the product of the maximum power voltage, often called VMP, and the maximum power current, often called IMP. This is the point where the module will produce the most power under STC conditions. On the graph here, the MPP is about 255 watts with a VMP of 34 volts and IMP of 7.5 amps. The area enclosed in the rectangle under the curve represents the power. Any other combination of points on the curve will yield a rectangle with less area and less power, especially as the current drops quickly once it moves beyond IMP. This IV curve, so here's the VMP you can see that corresponds to the maximum power point, and here's the IMP that corresponds to the maximum power point. These 3 points, the IMP, the VMP, and the maximum power point, are all operational. The system is actually producing when we see these. The IV curve also sometimes has a power curve imposed on it. Here we have the curve that just showed up that's kind of like a dark green color. All right. So here on the other side of the right side is the PV curve axis. So power is on the axis going up and down, and voltage is remaining on the side-to-side axis. So the IV curve has this power curve, and we can see power plotted against voltage. Notice that the MPP voltage of both curves correspond. The term fill factor describes the ratio of the peak power, so it's IMP times VMP, to a theoretical maximum power value obtained by multiplying ISC times VOC. Fill factor is used determining how well the module is producing and is compared to other modules as they age to detect degradation. In this example, the calculation shows a fill factor of 77.8%. IV curves can be measured in the field with relative ease. They are one of the best ways to determine how well a module or a source circuit are performing. Instead of having to guess or estimate how a module or string is operating under the existing conditions at a specific moment, the curve trace can be performed quickly to show exactly how a module or string of modules will operate under environmental conditions. The IV curve shows detailed information with a multitude of test points, which measuring just VOC or ISC alone would not show. When tracing individual PV source circuits, the IV curve will show an independent source circuit and how it would be performing regardless of the inverter. This could point to a problem with the inverter and not the string. It is also a good baseline for comparison of other similar strings of the same site. On a larger site, IV curves from a few controlled source circuits can be used as a baseline for the future, for comparison to strings throughout the same system and throughout the lifetime of the system. Lastly, IV curves of individual modules or strings are often required for warranty claims and other troubleshooting. They are one of the only ways to show hard evidence that a module is actually underperforming, or to diagnose particular failures that may be due to installation, shipping, or a manufacturer's defect. Bypass diodes are present to eliminate reverse breakdown voltage and hotspot failure caused from a reverse bias condition due to partial shading. If the operating current is above the reduced current of the shaded cell, the diode will begin conducting. Bypass diodes are usually located inside the module junction box. Most PV modules are built with 3 cell groups that have a bypass diode for each. This allows cell groups to be bypassed under certain circumstances and to protect the module from damaging hotspots. In this slide, we see bird droppings on one of the cells of the same module. Since shading or soiling of a single cell can cause the bypass diode to conduct and bypass the whole cell group, the PV modules are very sensitive to shading. In this case, the shaded cell would only be able to produce about 1 amp. With the bypass diode closed, more current is able to pass through the other 2 cell groups. Reading this IV curve, it is easy to see the notch that is on the curve caused by the shading and operation of one bypass diode. With the diode closed and the module operating at its maximum power point, MPP, that's the red dot, we can see approximately 1/3 of the module voltage is lost. At this new MPP, the VMP is reduced to about 16.7 volts and IMP is still 7 amps. The PMP is reduced to approximately 117 watts, down from 175 watts with the full module operating. If the module were to operate at the same voltage as the previous slide, where VMP is 26.3, note that the current from the module, according to the IV curve, would be only a little above 0.5 amp, and the power output would only be around 25 amps. Read from the power curve, y-axis on the right. However, with maximum power point tracking and bypass diodes, this module would instead operate at the indicated MPP and produce 117 watts instead of only 25. This loss due to the bird poop is less than 70 watts. Additionally, the shaded cell would experience heating from all the other cells trying to push current through it. If a solar cell isn't producing power with its current, it turns into a consumer and heats up. Bypass diodes can protect cells from overheating. Hooray for bypass diodes! Note that IV curves do not correspond directly to the module issue location. The IV curve sweep begins at ISC on the y-axis and ends at VOC at the x-axis. In the above graphic, the locations of the steps in the IV curve do not correspond to the cell group locations in the module. We'll see more about this in the coming example. IV curves tell us a lot about the modules and strings of modules and how they're doing, and they identify common PV array problems. Changes in the IV curve slope and notches can indicate various module issues and installation errors. If a PV array has an initial baseline IV curves, subsequent curves can be taken and compared and can quantify module aging and failures. The slides on bypass diodes describe module damage, shading, and other issues that can cause notches in the IV curve and mismatch losses, as shown in the red dotted line in this slide. These issues cause current mismatch in the cells in PV modules. We can also see shunt resistance losses that show up in as an increase in slope in the IV curve between ISC and the max power point. These shunt or reduce the maximum power point available and are due to compromised paths between the positive and negative sides of the PV cell. Generally, this is caused by a manufacturing issue, but it can show up as a change of slope here. It will show up as a change of slope in the IV curve. Another thing we can see in IV curves is the series resistance. This is seen as a decrease in the slope of the IV curve between max power point and VOC, caused by several factors such as insufficiently sized wire, loose terminals, corrosion at a module connection, excessive internal resistance within the modules, and aging modules. As long as the irradiance and the cell temperature are stable for the test and the test parameters are set properly, any of these deviations from a perfect IV curve indicate a problem that will reduce the max power available from that module or string of modules. Let's look at what we need to do to get usable IV curves during testing. First, it's important that IV curves be taken with adequate irradiance. If irradiance is low, the shape of the IV curve distorts and can mask issues. IEC standards require that the irradiance be at least 400 watts per square meter, and in some instances, 700 watts per square meter or more for testing to accurately see issues. In the field, these irradiances can be difficult to get, and there might be only a narrow window of time to take these tests each day, like between 10 to 2, for instance. High wind can also cause problems since the PV module cells can change temperature quickly when the wind blows, affecting the voltages of the test. The manufacturer's IV curves are taken at STC, which is the irradiance of 1,000 watts per square meter and cell temperature of 25 degrees Celsius. We will have to correct the field IV curves so we can compare them with the manufacturer tests. Therefore, it is imperative that the PV module cell temperature and irradiance at the module's tilt angle and orientation is recorded for each test taken, and these variables need to be stable for the test. Here's one manufacturer's environmental information gathering tool. There's an irradiance meter, also called a pyranometer, and a temperature thermocouple to tape to the back of one of the PV modules. The tool gathers the data and then transmits it to the IV curve tracer for computer for inclusion in the test data set. Also needed is data on the PV module that's available from the module spec sheet. We program the curve tracer to account for the module specifications so tests can be compared apples to apples. Now in this example, we are looking at one MPPT channel. It could be one of, say, 3 or 4 on a string inverter, or it could be a single MPPT channel on a big central inverter. The MPPT chooses one voltage to operate at, and it hunts for the voltage that will result in the highest power output. That's what's called maximum power point tracking, or MPPT. This example has 4 strings of modules on a single MPPT channel. All 3 of these strings are matched well, so the MPPT will choose a voltage. Now, the first 3, the bottom 3, the one with 7.1 amps at the maximum power point, are matched well. So the MPPT will choose the voltage that corresponds to the max power point or the knee of the curve to produce the most power possible. But let's say we have a 4th string that does not match the other 3. What voltage will the maximum power point tracking channel operate at? Looking at the module IV curve at the top, you can see that a notch is indicating that a bypass diode is bypassing a cell group within the module. Since only one module is bypassing a cell group, and there are several modules in the string, the notch is smaller than the IV curve than if we had tested just one module. If the IV curve for that string is narrower than the other strings, then the true max power point for the top string is at a lower voltage and current than the others. We aren't going to reduce the VMP for all 4 strings just to accommodate one string, because that would result in less power output total. So the MPPT will operate beyond the max power voltage for the top curve to get the best production out of all 4 strings. And the top string will have a resulting about 11% loss compared to if it was operating well. We could also see this effect if we use a clamp-on meter and measure each string and compare. Or we could read the current off a data acquisition system remotely. Let's talk about a specific example. Here's a PV array that is heavily soiled with bird droppings. There's a running joke about that the seagull is a patron saint of solar. Now, we expect the output of the array to be lower than it would be if the modules were clean, but how much is being lost? Is it worth the cost of cleaning modules to recover the lost production? In order to answer this question, we need IV tests. So we'll clean one module and then we'll test that one module before it's cleaned and after it's cleaned and see how much we gain. Now, looking at this IV curve, which we took, that's the IV curve we took with it dirty. And you'll notice those red dots at the top. And those red dots, there's 3 of them, and there's a red dot on the ISC of the original, the best, if the module was perfect and not soiled, that's there. And then this is the MPP of that perfect module. And then out here is the VOC of that perfect module. So we have a pretty poor IV curve here of a very, very soiled module. We'll also notice that the fill factor is 0.63 and the performance factor, which compares it to a clean module, brand new module, is 65.2%. Now, going to this, we see that we still have those dots for ISC, MPP, and VOC for a clean, brand new module. But now we've run an IV curve on the cleaned module, and it looks much, much better. We have our performance factor is up higher. If you get it over 100, there may be other things going on, like irradiance has changed a bit, or it's a little windy, or there might be these points might be incorrect in the software. So it's very important to get all those things correct. You'll also know that notice that the fill factor is up to 0.7, which is very similar to what we would normally find in a newer module. So by the curve, we can see that current is definitely affected by the soiling, and some cell groups are affected more than others. We also see a corresponding drop in the voltage due to lower radiance hitting the module. To compare, we can just clean one of the modules and we have cleaned the module and taken another IV curve. So that's the IV curve tracers. It's a very, very useful tool. It's sometimes done with, like in smaller systems, every string would have an IV curve tracer trace done. Some tools that are called string checkers also have a feature that it can also take an IV curve at the same time as it checks, say, the VOC, the ISC, does a insulation resistance test on the modules and the home runs. So let's switch to infrared cameras, IR cameras. This is a really great tool, and I have an IR camera at all the time when I'm in the field. I can check for loose connections, strings of modules not operating, hot cells, and other issues. I don't have to touch anything, so it is safer and faster than just about any other test I can do. I have a very portable and inexpensive plug it into your phone style IR camera that I carry with me just for taking a quick look, and a professional handheld style IR camera like you see in this photo in the upper right hand corner for more detailed views, or if I need to do warranty work or something like that. It is important to note that finding the exact temperature of something with an IR camera is very difficult and full of inaccuracy. What is pretty easy to see is the temperature difference. So here we're talking about qualitative versus quantitative. So if we're doing qualitative, we're just comparing two things that are in the photo with each other and seeing which one is hotter or which one is colder and by how much. That's qualitative. And that is something that's very, very easily done with thermal cameras, with a few things we have to learn. Whereas quantitative would be, we want a specific temperature. We want to know exactly what the temperature is. That's actually quite difficult to do for a number of reasons. And so what we normally do is that we do qualitative analysis with our IR cameras. With an IR camera, we are looking at infrared energy that is coming off an object. The energy can be emitted from the object, transmitted through the object, or reflected. Keep in mind that it's not like night vision, which amplifies available light. IR is not light and does not require a light source. IR thermography training, like the Thermography 1 certification that I have, is highly recommended for the PV professional. There are lots of tricks and tricky issues in interpreting IR images. For the amateur, or to begin understanding this useful tool, search the web for many free trainings available. Although many of us use handheld IR cameras, the latest trend is to mount a special IR camera on a drone or a fixed-wing aircraft and fly over big arrays. As can be seen in this photo, many issues can be seen at a distance in these large arrays. Pilots of these craft must get an FAA license and usually also own their equipment, so there are businesses springing up to provide these services in solar fields. Since hundreds of photos are normally taken, data handling and interpretation is a major part of their services. Just being able to recognize issues in the data set is a major task requiring deep skill set in data management, imaging, handling, pattern recognition, etc. We use IR thermography to detect issues in equipment from terminations to PV modules, and an IR camera is an essential tool for technicians doing troubleshooting. Here we are looking at the back of a PV module. You can see that 2/3 of the module is darker than the other third, indicating that the third is hotter. This indicates that one of the cell groups is being bypassed. In fact, if you look at the little junction box, that's the black box at the bottom that has the leads coming out of it, you can see that there's a small hot spot there, which is the bypass diode that conducting and producing heat. If we measured the open circuit voltage of this module, we would find that it's lower than it should be from its specs. And if we measured the operating current, we would see that the current is lower than it ought to be when compared to the two modules not bypassing. An IV curve of this module would also show an issue with a notch. This module would normally be in a string of modules and affect a single group out of an entire string, but maybe the effect may be too small to recognize. But when comparing different strings, this issue might be able to be picked up remotely by the data acquisition system data. So it's very useful to have these IR cameras. Here we've used the IR camera to image a group of strings as they terminate in a combiner box. Notice that we have an IR image and a photograph of the same equipment. Most IR cameras have an option to take both of these images at the same time. This setup is an option so that the detail in the IR image can be located in the photo with where the labels and the other details are visible. Otherwise, it might be difficult to pinpoint the problem in the real world. In this scenario, we expect all the strings to be carrying the same amount of current and therefore be at the same temperature. Yet we see that one is cooler. First, check how much cooler. Always look at the range at the right side of the image to see what the colors mean. What looks like a huge temperature difference may just be that the range for the image is narrow. We may suspect a blown fuse for that string and can troubleshoot using a clamp-on amp meter. In order for issues to show up in IR images, we need enough current flow to have a wide temperature difference between items that are functioning properly and those that are not. For PV system components, we need the irradiance to be high enough for the system to be producing well, and for the other equipment, we want it to be operating at least 40% of its rated load. Also be sure to allow times things to heat up after the system is turned on before taking these important IR images. As mentioned earlier, reflections can show up in IR images, and they will often mask or interfere with detecting the actual temperatures of things. A typical example is the reflection of the sun, which at certain viewing angles can look just like a module hotspot. A trick to detect reflections in an IR image is to move the camera around. If the supposed hotspot moves when you move, then it is actually a reflection. In this photo here, we see two wires coming into lugs in a piece of equipment. This could indicate that the colder wire on the left isn't carrying as much current as the wire on the right, or that the wire on the right has a loose connection. We see that the wire on the right has a gradient, a temperature gradient on it, showing that it's hotter at the lug and cooler as the wire gets farther from the lug. This indicates that a loose connection on the lug is likely. In this instance, the power hasn't been on long, and if we took another image later, the lug would also likely be hot. Remember when we are looking for temperature differentials mostly, and sometimes a cold item may indicate the issue. If the system has been operational for a while and everything looks hot, and the cause just isn't apparent, then a good way to troubleshoot is to turn everything off, let it cool down, and then turn it back on and watch what gets hot first. So let's look at some aerial images and check out some of the issues that are easy to see from the air. First, we can see that two strings show warmer than the others, right here and over here. When the module or string is not operating, it is warmer than it would be in operation. This is because in operation, energy is going down the wire and coming away from the module, and that the energy, when the module is not working, just heats up the module. These strings could have a blown fuse in the combiner box, or they could be disconnected somehow. Like, for instance, if a module connector was not fully seated. Now here and over here, we see that there's a diode bypassing a cell group in PV modules. Now this could be due to soiling, or it could be module damage. Sometimes hot module cells can also be seen at this scale, and sometimes we need to zoom in to see that better. All this is in the data, however, and most of the issues in aerial images are analyzed using data analysis tools as opposed to just simply looking at the images. Here's an IR image of a hot cell due to a bad solder joint inside the PV module. And this patchwork pattern results from a short-circuited module. The cells aren't perfectly matched, so at ISC, the mismatch of the cells becomes obvious as the higher performing cells push current into the lower performing cells, heating them up. There could be an internal failure in this module, or the leads of the module could be plugged in together in error. These aerial images make fast work of locating issues in large arrays and are an important tool used by smart technicians. They are the beginning of troubleshooting, and as easily they pinpoint the effect of the issue, but additional testing is often required to find the actual cause. Here we show a chart derived from ANSI, NETA, MTS, and FPA 70B, that's NFPA, summarizing the suggested actions for issues in IR thermography. Mainly, the severity of the issue is determined by comparing two similar parts' temperatures and acting depending on the temperature differential. For instance, if two wires have a 3°C temperature difference, this chart suggests, so that's over here, this chart suggests possible deficiency warrants investigation. So we would go in and do some investigation, but we might not act on it. If the difference was greater than 15C, however, it is suggested that the discrepancy be investigated and repaired immediately. This is because heat can destroy equipment, cause arcing, and start fires. This chart also suggests to compare the isolated part temperature with the ambient temperature. If an electrical part is hotter than the ambient, then it may indicate an issue because most electrical equipment is designed to stay fairly cool. But note that PV modules often operate at 25 to 30 degrees higher than ambient temperature, so it doesn't make much sense to compare them with ambient temperature in an IR image. This is a resource that shows the effects of common PV module issues in IR images. A properly operating module will have slight differences in cell temperature, as seen here. Here we see a module overheating where the entire module is hotter than others. The module is likely at open circuit voltage due to a blown fuse or open connector, or the module might be disconnected. If we see part of a module that is hotter, we suspect either diode failure, a junction box issue, or that the cell group is being bypassed for some reason. Note that this sample module only has 2 cell groups, and most modern modules have 3 or even 4 cell groups. Now, if a single cell shows up hotter than the rest, then this can be a result of shading or soiling, where the cell doesn't cause the bypass diode to actually bypass because it is only a small part of the cell group. Or it can indicate module failures. A patchwork pattern of cell temperatures, as we mentioned before, is due to module operating at short circuit current. And finally, part of a cell is seen overheated. This is often due to a cell defect, possible spot shading, an internal module issue, or a manufacturing defect. As with a single hot cell, where the part of the cell is small enough, it may not cause the bypass diode to actually bypass. So the insulation resistance testing, sometimes called IRT or MEGGERING, is another important tool for us to use. Sometimes called a meggometer, it can be used to test the integrity of conductor insulation, and this is another test that is highly recommended before commissioning and when troubleshooting systems. This is a standard tool electrical contractors use to test conductors in insulation integrity. Similar in idea to a radiator pressure test, the conductor insulation is pressurized with voltage to make sure there are no leaks in the insulation. The meggometer generates high voltage, low current signals far in excess of those from a handheld ohm meter. If conductor insulation is compromised, meaning that there's a path for leakage current between the ungrounded and grounded conductors and ground, the meter will show a low resistance reading indicating that a problem that must be addressed before operating the circuit. Insulation testing can be performed on any conductors, but this focus is on PV array wiring, both source and output circuits. Before performing the test, confirm voltage and polarity of the circuits. Next, the DC system ground must be physically broken, meaning that the grounding conductor is removed from its connected point to ground. We'll go over this in detail. A low resistance reading means there are problems with the conductor insulation. Initially, the test can be performed in a combiner box, for instance, with all the fuses removed and the negative output conductor from the combiner box lifted. Or if your combiner box breaks both the positive and negative of the array, sometimes we can just use either the fuse holders oftentimes and not have to lift the negative. If a meter reveals a problem, then the negative conductors of individual source circuits must be lifted off the negative bus bar in the combiner and tested to isolate the problem. That's if the negative doesn't have a fuse. Be aware that environmental conditions, namely temperature and humidity, affects this temperature measurement, affects the measurement greatly, and should be logged for each test so that the results can be compared along with test voltage and the test result. It is highly recommended for all conductors to be tested with a megometer prior to being landed in equipment. That way, subsequent tests can be compared to the baseline for reference. For the PV source and output circuits, there's a special method for this test or special equipment like the Seaward 210, for instance. We will cover that in another slide. These tests are required by IEC 62446 and are a normal part of commissioning PV systems. This insulation test detects when the conductor insulation is compromised, even if it is inside conduit, underground, or otherwise hidden, so it is a very valuable test. It is also used to detect ground faults, and in the case of intermittent ground faults, the array or boxes can be hosed down so that they are wet. Since water conducts electricity, if the array and outside wiring are wet, it can reveal a hidden ground fault that only occurs, say, when it rains. These intermittent ground faults can be caused by intermittent conditions, such as a rainy day, as I mentioned before, maybe a junction box fills with water, or a particularly hot day, which causes the compromised insulation to soften around the edge of a metal conduit. Again, it is standard electrical practice to do insulation resistance, and sometimes we call it meggering, for all conductors. The test is always between two parts. The example is testing the red conductor to ground, but all combinations must be tested for a complete test. For instance, say we have a metal conduit with a red and white wire in it, as in this example. We would have 3 tests: red to ground, white to ground, and white to red. An example of a problem with IRT we'll find is if the conductors were pulled in the conduit and some of the insulation was skinned off one of them, the wires, around the edge of a sharp metal conduit. This test can catch that problem and allow it to be resolved before it causes more problems in the system. Prior to testing IRT, it is important to test the ground continuity. If the ground is not continuous, the results can be false, negative. In other words, it can not catch an actual problem. This slide shows that the value of this test between the red wire and ground is 3 gigohms. This is a good result and indicates that the conductor insulation is good. So let's look on how we can evaluate IRT results. This is from the ANSI-NIDA testing table. We also referred to the manufacturer's recommendations, and we can refer to the ICEA for minimum acceptable resistance values as well. Keep in mind that IRT tests are done at different temperatures and can be compared with using published correction factors for temperature. To use this chart, take the nominal rating of the equipment being tested and use the test voltage to indicate it in column 1. Let's say that I had a 120 volt circuit in a house, like a regular receptacle circuit, and I wanted to IRT test the wires, and then I would set the tester to 250 volts, and then I would expect nothing less than 25 megohms to come back to that from that test, or else there's probably a problem. So for instance, for PV, let's say that we have a 600 volt nominal rating, like on the DC side of a residential string inverter. I should see 100 megohms in the test result or more for a good result. We also compare the results of the IRT for like wires and flag the outliers. Wires of the same size, insulation, and length should have similar IRT values. In PV, we do IRT tests that are unusual for the electrical industry. We actually test energized circuits. That's because our PV array will be energized if the sun is shining. We put the IRT tester in series with a string of modules, with the red or positive meter lead going to the negative of the string, and the black or negative meter lead going to the ground of the array. Again, the ground needs to be continuous for this test to be valid. The positive from the array is isolated either by turning off a disconnect or by lifting it or capping it off. During this example test, the meter will apply 500 volts to the module's and array wiring, pressurizing the circuit all the way around through the positive wire. If anywhere in the circuit there is compromised insulation to ground, a low resistance reading will result. Testing in this way will allow us to see if there's an insulation problem anywhere in that circuit. Now, warning, this is an energized circuit and we are pushing high voltage into it, so the proper PVE and safety protocols are essential. Note that the PV module manufacturer must approve of insulation resistance testing before we test their modules. The IEC gives us guidance on testing voltage and minimum insulation resistance values for PV source and output circuits. To pick the testing voltage, multiply the VOC by 1.25. The first category shown for the system voltage is less than 120 volts. And an example of this is maybe a single module connected to a microinverter. We would use the test voltage of 250 volts, and an acceptable test result would be half a megohm or more. A 600 volt residential string inverter would fall into the last category, above 500 volts. In this case, we test at 1,000 volts, and a passing result would be 1 megohm and greater. Again, not only do we need to compare the test results to these guidelines, but we also want to look for outliers in the results and compare like circuits to like circuits. Now, an update has just been released for the IEC 62446, and there are new values for above 500. When we get a ground fault indication, we use insulation resistance tests to pinpoint the fault. For instance, if we have 3 combiner boxes, we test each one as a whole. And if one doesn't pass or it looks like the other, doesn't look like the others, we test each string in that combiner box until we find the string the fault is in. Then we use a multimeter to isolate the location of the fault within that string. This works especially well in the case of hard faults or low insulation resistance values. We'll take a look at the method in the next slides. Ground faults can happen for a number of reasons. For instance, a home run or module lead can get pinched between the racking and the module frame. Conductors that are expanding, contracting with temperature changes can rub against sharp edges and damage the insulation. Or maybe a junction box fills with water, shorting the conductors to the grounded metal. Sometimes we need to wet the array down to find the issue, or wait until the condition associated with the fault happens, like the wind blowing from a particular direction. These skills are an art and science. Go to troubleshooting ground faults with strategy and a safety plan, knowing that all the metals of the system, even metal conduit and racking, could be energized and cause shock danger. So in this example, we did IRT tests on the combiner boxes. We found the string with the issue and are using this technique to find the ground fault within the string. As with all types of troubleshooting, being methodical and taking careful notes will pay dividends in the end. First, check to ensure that all modules are wired correctly. Perhaps a wire was switched in a combiner box or landed incorrectly in a disconnector inverter. Check for pinched wires between panels or in conduit. This can be difficult when wires are located behind modules or when conductors have been skinned during installation and the damage is hidden in conduit. Check for junction boxes that are filled with water and for loose connections on terminals. Now, if nothing obvious has been found, then the next step, turn off the system with the AC and DC disconnects. Now, you got to wait for those DC input capacitors to discharge, which is usually 5 minutes for residential sized inverters, although this can take longer with larger inverters. You can use a multimeter on the inverter input, the DC side, and make sure that the voltage is 0. The next steps may vary depending on what type of inverter and what conductors are switched in the DC disconnect. Newer systems can be easier to troubleshoot since many of them are transformerless, non-isolated type. In these, there is no ground fault fuse. Regardless, though, of inverter type, we need to isolate all DC conductors, including the ground, from the electronics, such as the inverter, surge protection, and the data acquisition system. If these are left in the circuit under test, the equipment will likely be damaged by the high voltage of the IRT test, and the test will not have valid results. For newer transformerless non-isolated type inverters, double check that the DC disconnect is off and verify the lack of voltage in the inverter. Some of the disconnects switch both positive and negative, and others only one of the current carrying conductors. Determine which one you have. If the disconnects switch both positive and negative, then thank your lucky stars. All that is required is to switch off the disconnect, and that disconnects the positive and negative conductors. If the disconnect only switches one conductor, usually the positive, then check that there is no voltage at the inverter. Now there's danger here. If there is a ground fault, and then there could be voltage between the negative conductor and ground. So you need to know what you're doing here to accomplish this safely. Carefully remove the grounded conductor or conductors, typically negative, from the DC terminals inside the inverter and cap them off. In legacy systems or central inverters, many have an isolated inverter that has a ground fault fuse. If so, follow these steps. Remove the ground fault fuse from the inverter. This may require removing the inverter cover. Then check the fuse for continuity. If the fuse is blown, meaning no continuity, then there most likely is a ground fault in the system. Then double check that the DC disconnect is off and verify lack of voltage in the inverter. Danger! If there's a ground fault, then there could be voltage between that negative conductor and the ground. You definitely need to know what you're doing to do this safely. Carefully remove the grounded conductor or conductors, typically negative, from the DC terminals inside the inverter and cap them off. This step is necessary because there's typically a high impedance connection through the electronics of the inverter between the ground and grounded conductor. This next step, though, is the same regardless of the inverter type. Measure and record the voltage between the positive and negative conductors at some point outside the inverter. Typically, this would be on the DC disconnect. The value should be open circuit voltage for the array. Then measure the voltage and polarity between ground and the PV positive conductor. Again, this will typically occur in the DC disconnect. Measure voltage and polarity between ground and the PV negative conductor. Compare the readings. With the conductors isolated from the inverter, these values should be 0. Since there shouldn't be any reference or voltage potential between the PV array and ground. Likely it won't be 0, however, indicating a ground fault. This is an example of finding a ground fault using the procedures outlined on the previous slides. A digital multimeter and the proper personal protective equipment is required. At this point, the ground fault protection fuse has been checked for continuity and the grounded conductor has been lifted from the inverter DC terminal. If testing in the DC disconnect has shown that there's voltage between PV negative and ground or PV positive and ground, then the next step is typically to test in the combiner box. Remove the fuses and disconnect the grounded conductors from the common bus bar, and then take the measurements as outlined below. First, check voltage between the PV positive and PV negative. The result here is 400 volts. Divided by 10 modules, this means that each module is adding about 40 volts to the circuit. Next, check the voltage between ground and PV positive. In this case, let's see, the result is 0. Next, check the voltage between ground and PV negative. The result is 0 volts. Here, there is no ground fault, or there could be an intermittent ground fault. Here's another example. Check voltage between PV positive and PV negative. The result is 400 volts, just as before. Divided by 10 modules, this means that each module is adding about 40 volts to the circuit. Next, check voltage between PV ground and positive. In this case, the result is 280 volts, or 7 modules worth of voltage. Next, check the voltage between ground and PV negative. This result is 120 volts, or about 3 modules worth of voltage. This means that somewhere between the 3rd and 4th or 7th and 8th modules in the string, there's an issue. PV positive to ground is 280 volts. That means that the negative is connected to ground 7 modules from the positive end of the string. Likewise, PV negative to ground is 120 volts, so positive is connected to ground 3 modules in from the negative side of the string. These are 2 spots are the same. If the fault is 3 modules down from the top and 7 modules up from the bottom, likely there's a pinched or rodent-chewed module interconnect. Here's another example. Again, the voltage between PV positive and negative is 440 per module. A test from positive to ground returns a value of 360 volts. Let's see here. There it is, 360 volts. You can either count up from 1 module from the positive end or count down 9 modules from the negative end to locate the module with the ground fault. A test from the positive to ground is 40 volts. Note that ground fault on roof-mounted systems can be difficult to find. It's hard to see behind the PV modules, and sometimes there are not walking paths to allow good access. As I mentioned, locating ground faults can be challenging, time-consuming, and dangerous. High voltage may be present between conductors or metal surfaces that are usually not energized in relation to each other. Remember to follow all proper safety procedures and wear the appropriate personal protective equipment. In this example, the voltage between PV positive and PV negative is again 400 volts, 40 volts per module. PV positive to ground is 0 volts and PV negative to ground is 400 volts. This means that PV positive and ground are connected together somewhere outside the string. In this case, there's a fault between PV positive and a grounded piece of metallic conduit. Right there, somewhere close to the combiner box or between the combiner box and where the home run connects. That was a quick look at ground fault troubleshooting. I want to leave you with a list of relevant codes and standards. So the first one is NFPA 70E, the standard for electrical safety in the workplace. Also 70B, required practice of electrical equipment maintenance, and this covers general electrical equipment as well as some PV system work. There are also several IEC standards for our work. I mentioned earlier IEC 62446. It's an international standard that covers the minimum requirements of system documentation, testing, and inspection when commissioning a grid-tied PV system. They've just released a new version of this, IEC 62446. Also listed is the ASTM standard. Only by the provision of adequate documentation at the onset can long-term performance and safety of the PV system be ensured. Well, I want to thank you for your attention to this presentation, and I really hope to see you, maybe online or hopefully in the future in person. Maybe we can resume face-to-face classes in the next season and start going to conferences again. I just really hope that our paths cross again. Be sure to go on solarenergy.org website and check out our classes. And don't forget those discounts that we've made available. Thank you so much, and I hope this helps you.
Hello, and welcome to this course on the physics of solar cells, what goes on inside to actually make them work, and how come the IV curve is shaped the way it is. I'm going to go through all the physics of that, but don't worry, don't freak out. It's not going to be with heavy equations, and it's going to be fun, I promise you. My name is Mark Morose. I've been involved in solar my entire working life, and I think we're going to have a good time in this course. At SEI, we offer in-person as well as online courses. And because of the COVID-19 epidemic, we have established a global solar connection initiative where we've stepped up our game in terms of the offerings of our courses online for you to be able to easily and safely take all of our training. A special offer for all SEI attendees, we're offering a $50 discount off of all of our regular 6-week online courses that you can take all the way from our beginning 101 course all the way through our most advanced 350 course on operations and maintenance, which has recently been fully updated. And also over the last 3 years, we've received 3 grants from OSHA to develop safety-specific courses. And we're offering a super discount on those, only $99 for the 2 courses that we have up live now. That's basically 1/3 of the regular price. And there's also a 3rd new one on battery safety, which is now free for all members of the US that are covered under OSHA. So please check that out as well. And we offer a wide variety of on-demand courses that you can take anytime at your own pace. These are all available at our website, solarenergy.org. Now let's jump in to the course on the physics of solar cells, and I'll begin with a bit of an introduction. I started my career making solar cells, and I haven't ever stopped. So upon graduation from college with a degree in physics, I started at Spectrolab, actually in 1974, making space solar cells. So this was right around the oil embargoes and so on. This was way before terrestrial solar was even the gleam in anyone's eye. But after Spectrolab, I joined and started with Arco Solar, the Kleenex of solar back in the 80s. And that became Siemens Solar. I joined AstroPower. That became GE Solar. And then I joined SunPower and created the entire residential training program there from 2005 to 2010. Then joined EcoFirst and learned a great deal about solar thermal and PV together. And that was bought by SunEdison. So I rode that rocket. And then I joined Interplay Learning, where I have been helping create an online virtual curriculum in 3D and VR space where you can actually assemble a solar system together in virtual reality. And now I'm working with Solar Energy International. So I've matured a bit in my life, learned a bit more about things, but have always still been in love with solar cells and IV curves, and hopefully that will come across to all of you. I'm going to cover these kinds of topics, so keep this in mind in terms of the arc of what we're going to go through. I'm going to go through some actual physics stuff here, but without equations to scare you away, but it's actually going to be real physics. So I know a lot of us deal with this stuff. Solar is wonderful. We know a great deal about it, and we know how to use it and sell it and that it works. But often we don't have the time or the inclination to know, like, what's the guts inside? And maybe this will be the one and only time that you get to explore this stuff, then you can put it on the shelf. But I wanted people to be able to be exposed to the whys of how come this stuff magically works. What is the magic behind it? So we're going to start out by talking about why we dope a solar cell, and then review the current voltage curve, which, by the way, I'm not going to dwell on in terms of the 5 points, but I am going to spend the time of this course heavily focused on IV curves. Then we're going to mention the equivalent circuit of a solar cell in case you're not familiar with that, because that's going to help to explain a lot. And then I'm going to jump into some actual quantum physics of band gaps, which is what you see here. And it's going to help to explain some things that perhaps you've heard, perhaps you haven't heard, about how come this whole thing works. And then the whole focus of what I wanted to do in this talk was to explain how the IV curve gets its shape. How come it's shaped the way it is? We maybe know it and love it and use it, but how come it has that shape? It's pretty interesting. And then cover some environmental effects that we're all familiar with. For example, solar cells and modules lose voltage when they get hot. But why? What's the physics inside of how come it does that? That's what we're going to cover. And we're going to finish by dealing with the effects of shading on that IV curve and what I call the dolphin nose effect to the effect of shading. So that's what we're about to embark on. So let's get started. So why do we dope a solar cell, and what does that even mean? So silicon rocks on the left-hand side. The silicon is the second most abundant element on the Earth's surface next to oxygen. And silicon and oxygen together make quartz, which is sand. So there's lots and lots of silicon. The key thing that we're going to focus on here, and I'm going to go from simple to complex pretty quickly. The key thing here is that silicon has 4 outermost electrons. It's got a nucleus with the protons and the inner electrons and so on. And then it's got these 4 outermost electrons. They're called valence electrons. These are the ones that are used in bonding, making crystal structures. These are the ones that are exposed and can link to other atoms and so on. The key thing here is that it's got 4. So what's that going to mean? Well, it means that every silicon atom, when you grow a crystal, is going to link up with 4 other silicon atoms. The figure on the left is the actual face-centered cubic structure that we get. In fact, the structure of silicon crystal is the same as that of a diamond. It's just that uses carbon and this uses silicon. But carbon also has 4 outer electrons. So this would be the 3-dimensional structure of that silicon crystal lattice. What I'm going to do is draw it flat like this with all of those 4 bonds, and you see that every silicon circle atom is bonded to 4 other silicon atoms in a crystal, okay? So now let's proceed to understand what happens when you take a hunk of silicon and put it in the sun. Just take a rock of silicon and expose it to sunlight. What's going to happen? We're going to have what's called whole electron pair creation, and this is how it happens. You have a particle of light, which we call a photon. So we can think of light both as being a wave, that can bend, and you can bend it through prisms, but it also can be treated as particles, and we call those photons. A photon of light comes in, and on a random basis, it hits an electron in the silicon bond and gives up all of its energy. It goes away, and all of its energy goes into energizing that electron. And it gives it enough energy to break free. It basically ionizes the electron away from that atom, and now it's got enough energy to break free. It's no longer bound. It's now a conduction electron, and it can move through the crystal. But what happened? Everything was electrically neutral before that happened. But as soon as that electron is gone, you've now left a silicon site without a balancing electron, negative charge. So you've got a net positive charge in that area. And physicists have come up with a pretty complicated name for that. It's called a hole. It's like a bubble in water. It's a hole in the crystal structure where a charge could be, and it carries a positive charge. And this is what happens now. Just at room temperature, nearby electrons that are vibrating, running around, they're normally bound in those bonds, but it can vibrate enough, and it can vibrate over and fill that hole. And so now that covalent bond is now full, again, with 1 electron being shared by each silicon atom, so it's filled with 2 electrons, but it got filled back up again. But what happened? It left behind a space where it came from. And that now also carries a net positive charge because the silicon site has the same number of protons, but it's missing 1 electron, so its net charge is now positive. And then what can keep happening? A nearby electron nearby can vibrate, fill that hole, but then the hole is moved to another site. So what's happening is that we've created 2 free carriers of charge, electrons that carry negative charge and holes that carry positive charge. And these are now able to move around within the silicon crystal structure. Now, what can happen though is that lots of those electrons can wander into those holes and recombine and fall back in. And basically, you can have light come in, knock electrons loose, they recombine, and nothing comes out. All that happens is that the silicon rock gets hot in the sun. We don't want that. So the trick of everything I'm going to tell you now is going to be about how we design solar cells so that when those electrons get knocked loose and free, we get them out of there before they can recombine with the hole. That's the whole trick behind every solar cell that's ever made, no matter what it's made from. That's the main idea. I'm going to talk about silicon because it's used to make about, 95% of the world's solar right now. So it's pretty indicative, but the principle is true for everything. So now let's keep going. So how are we going to do this? How are we going to create a structure that sweeps out those electrons? Well, this is how we start. One way we're going to do it is to introduce the element boron into the crystal structure. What happens is that when we grow crystals, we melt rocks of silicon and they put in a little bit of very pure boron at that point. Then you close up the crystal grower, melt it, grow a big crystal, and the boron is sprinkled throughout. The key thing about boron is that it has 3 outermost electrons. That's what's the important thing about using boron. So when it fits in the structure, it will easily share with 3 other electrons, no problem. But there will be this 4th bond, this 4th covalent bond, that now only has 1 electron from the silicon, but it doesn't have an electron from the boron. There's nothing wrong. It's all electrically neutral. Everything's fine. But there is a space in which an electron could fit, okay? So now what's going to happen? Okay, you've got electrons vibrating nearby. They're going to be able to vibrate over and jump into that hole, and they'll fill it up. Now, excuse me, it wasn't a hole before. It was a spot in which an electron could fit into a neutral site. But now it brings with it a negative charge, and that charge stays there forever, day and night. This has nothing to do with light. So that electron moved over, and now what happened? It left behind a space where it used to be, which used to be neutral, but now it's got a net local positive charge. And then what can happen? Just like we saw, that hole can vibrate from site to site and can move around in the crystal. So what we've done by introducing boron is we've introduced particles able to carry a positive charge that can move around within that crystal structure. And so that's why this type of silicon is called p-type, positive type. The carrier, the free carrier that's able to move around here, carries a positive charge, even though it's basically an absence of a negative charge. It's like a bubble in water. So this is boron doping p-type. Don't be confused to think that we've somehow made a different kind of silicon. It's like p-type silicon is different. No, it's describing the crystal structure of regular silicon that has this dopant in it, okay? And don't forget that the boron site now has a permanent negative charge. This charge now is held in place. It can't move around like that hole. It's held in place. That's going to be important. Let's keep going. What do you think the other element is that we introduce? It's phosphorus. What do you think its characteristics are? The way that phosphorus is introduced is that now we take the big crystal that we grow, we slice it into very thin wafers, we put them into a diffusion tube, which looks like a big torpedo tube. It's about 1 foot in diameter and glows red hot. And into that is introduced a gas that contains phosphorus. And the heat is so high that the phosphorus atoms basically penetrate into the crystal structure and take the place. And when they do, phosphorus has 5 outermost electrons. So it has 4 electrons to share with the 4 silicon atoms, no problem. But the 5th electron basically is just dangling there. And even at room temperature, it has enough energy to just break free. And that electron now can just break through and wander in the crystal. So now we have silicon crystal structure that has particles able to carry a negative charge. And so that's why this type of doping is called N-type silicon, because of the negative type charge carrier. And now, just like before, the phosphorus site now has a permanent positive charge because an electron's been stripped away. It was neutral, but now it's stripped away. So it's missing the negative, so it's got a net positive charge that stays right in place and doesn't move day or night. That's going to be important. So let's do something with this. Let's put these guys together. So basically what we have here at the front, if you can see my arrow pointing around, the N-type region, typical for most cells, the N-type region is what's going to be the front of the cell. This is going to be facing the sun. The P-type region is going to be the bulk of the cell in the back of the cell. So let's do this. Let's introduce phosphorus to the front of the cell, which has its spare electrons that it's going to let loose. And let's build that in front of the bulk region, which is filled up with boron atoms that have these sites that could accept electrons. Now, just a note about this, typical solar cells, and different cells are made differently, but typical silicon wafer solar cells, this N-type region is pretty thin. A solar cell today is anywhere from, I don't know, 150, maybe 200 microns, 180, maybe 150 microns thick, pretty thin, but 150 microns. This front region is typically 1/2 of a micron out of the 150. So the front region of the cell that has this N-type magic is pretty darn thin. And we're going to see that light actually goes right through it, okay? But here's what happens, okay? In those diffusion tubes, when the phosphorus is being introduced in the dark, those electrons start breaking free and they wander and they find these holes and they go, great, this is a place where I could stay. And it goes and it stays forever. So what happens is that you strip electrons away from the phosphorus sites and you embed them and leave them in the boron sites. Now, when it left the phosphorus, it leaves a localized, fixed positive charge in the crystal. And where the electron went, it brings with it and holds a net negative charge in that area. And there's trillions and billions and zillions of these happening. So you build up a region of positive charge on the piece type, and then gradually as it moved over, you build up this sort of region, vertical, sort of a flat region of negative charge on the boron site. And this separation of charge creates a permanent electrostatic field that's created across the p-type, n-type junction, or the p-n junction. It's this electrostatic field that is the magic that we've been trying to create. We're going to see that this is what makes the solar cell work. And the magic of using semiconductors is that they are crystalline, so that when we do stuff to them, they hold the charges in place. It's not like doing it in copper or some sort of conductor where the charges just move around however they want. These guys get held in place. And that's the magic, one of the many magics of semiconductors. So now, let's finish off this discussion by looking at what we've done. So remember, the front of the cell is pretty thin. It's, light can just go right through it. It's so thin. So let's now take this doped wafer of silicon and put it in the sun. Remember what happened before? It just got hot. But now a photon of light comes in, actually penetrates through the front, goes into the bulk of the cell. Think of the bulk of the cell as just being an absorber. It's just a bunch of silicon along for the ride with a bunch of electrons that can be hit by photons. So it gets hit. The electron and hole get created, hole electron pair creation, remember? And that electron just starts wandering free. Remember, it just got knocked loose. And if it wanders into the field, we can deal with it. One of the sources of inefficiency of solar cells is that those electrons can wander the wrong way. And they can wander until they find a hole and recombine. So that's called electron hole annihilation or electron hole recombination. And the recombination current is something that manufacturers try to make small. They try to get the electrons out, but some of them recombine. So that's one of the sources of the fact that we're not 100% efficient. But if the electrons wander into this field, as soon as it does, it feels negative behind it, pushing, because light charges repel, and positive in front of it, pulling, and it gets accelerated out and pushed out to the n-type region and pushed to the front of the cell. And it happens pretty quick. And that's the key. Now we have a mechanism. The electrostatic field is like an electronic broom that sweeps electrons one way and gets them out of there before they can recombine with the holes. And then the hole, remember, also has a life, and it can wander. If it happens to wander this way and wanders into the field, it feels negative charges pulling it back and positive charges in front of it repelling it, because light charges repel. So it's repelled basically backwards, and it basically migrates to the back of the cell. And we're going to see this in future slides. So basically we have now a separation of charges with the electrons being pushed to the front and the holes being pushed to the back. And that's exactly what we wanted to make a solar cell work. So now let's put this together. Now I'm going to jump ahead and explain that a solar cell net voltage is about 1/2 volt. And we're going to learn about this by physics in a minute. But the voltage of a cell is about 1/2. That's not much, okay? So we end up wanting to put cells together in series to add voltage. 1/2, 1.5, 2, 2.5, 3. We make them into 40 and 60 and 72 cell modules. So let's look at what's going on there. Let's follow the physics here. Let's remember that we've got an electron in the silicon just sitting there, stuck, right? Ready to go. It's exposed to sunlight. The light comes in through the front, gives up its energy, creates a whole electron pair. The hole, like we always know, is going to wander, and it wanders to the back. And I'm just going to show another one here, just because that happens in all the cells. This is all going on at the same time. But the electron wanders, and hopefully it wanders into the field. And when it does, it gets pushed out of the cell, and we've gotten that electron out. So now we've converted sunlight into electricity. Yay! And the net gain is about 1/2 volt. We're going to learn more about that later. But we end up coming out with electrons with about 1/2 volt. But now, this is important. what happens is that now that electron is connected by interconnect wires to the next cell. It flows into the back of the cell, finds a hole, and falls into that hole and stops. The electron does not keep going. It's not like the light came in, knocked an electron loose, and it goes whoop, out and goes to the inverter and does its job. No, it just goes to the next cell and it stops. It fills a hole and it stops. And it says, okay, I'm here. What has to happen is that you have to have another photon of light, knock it loose, the whole electron pair gets created, the hole wanders to the back, the electron gets pushed to the front, but now it came in with a half, it gained another half, so now it has 1 volt, and it keeps going through. And as it goes through cells, it gains a half a volt at each step. But the critical thing here that has to do with shading is that all electrons have to be regenerated in each cell equally. So you have to have effectively the same number of photons hitting all the cells so that simultaneously electrons can leave one cell, go to the next, leave that cell, go to the next in a flow. That's why shading is so important, because if you cut down the number of photons in one cell, you've got all these other electrons coming in and you don't have enough photo-generated current going out, and you get the dolphin nose. And we're going to get to that at the end of the lecture. But there's the idea, is that electrons go from cell to cell and they stop, and they have to be regenerated with this whole electron pair phenomenon. Let's finish up by putting it together. So now this is physically what cells look like connected, right? With the interconnect ribbons going from the front of one cell to the back of the next. Well, typically you use ribbons. They could be flat ribbons, they could be round ribbons, they might even be shingled. The basic idea here is that you're connecting the front of one cell to the back of the next. Why is that? Because you now have this flow where light comes in, knocks electrons loose, they go to the front of the cell, get into the ribbon or the interconnect somehow, flow, go to the back of the cell and stop, and are regenerated in that cell by new light, which then go to the front of the cell, go in the ribbon, go to the back of the cell and stop, and so on. So that's the actual physical look at how the electrons flow from one cell to the next in series, right? So we're getting to the idea of what we all know, which is how these guys are connected together and what's flowing. Let's put it all together into a complete module. Let's say you have a 72-cell module. So you have 72 cells in series, 72 of these processes going on, and roughly after going through about 72 and gaining roughly about a half, you end up with, let's say, 40 volts as your typical operating voltage out of that many cells. And then if you want more volts than that, you connect those together. So if we have a long string of modules, you basically have hundreds of solar cells all connected in series, adding 1/2 volt at a time, right? So now we're going to look at the IV curve, and I'm going to start quickly because I expect everyone to be pretty familiar with this. So the red curve is the IV curve, the relationship of current to voltage. The key thing here, the key thing I'm going to say 1,000 times, is that an IV curve is a curve of possibilities. It's a curve that describes current voltage pairs. So a module or a cell cannot simply operate at any current and any voltage. It's only specific currents and specific voltages given the environmental conditions. That's what the curve's going to tell us. And what we're going to learn is how come it has that shape, okay? But this is the typical curve. There's also a power curve that you can draw as well. And it's got the short circuit current, open circuit voltage points. I'm going to move on from this because I assume most of us are familiar. What I'm going to emphasize here, though, is that the solar cell is a passive device. Where it operates on the curve depends on its load, on what it's connected to. The module doesn't tell you where it operates, the load does. For example, simple case would be connecting it to a battery, some sort of battery. In this case, maybe a 12-volt battery. The 12-volt point tells the module to operate at this point on the curve, which happens to be pretty close to short circuit current. But it's the module, it's the load voltage that tells the module where to operate, not the other way around. Now we know that given this condition, a module will charge up a battery and its voltage will rise and it will move along the curve. But it's the battery telling the module, oh, I'm a little more charged, I'm now at 12.5 volts, okay? Different example would be connecting a module or a cell to a resistive load, let's say a heater, okay, or a resistor. And there again, I draw in another curve. This is a line of resistance. And for those not familiar with it, I'm going to use this again later, but this is a curve that shows a resistor line. At a certain voltage, you get a certain current. Double the voltage, you double the current. That's the line of the resistor. And where the line of the resistor intersects the line of the IV curve, that is the operating point of the system, of the two of them together. So whatever that resistor is, wherever it hits the curve, that determines the voltage and the current that you get out of the module through the resistor, okay? For example, in order to operate at our max power point on the knee of this particular curve, I would want a resistor of about 3.5 ohms. That would give me the maximum power from this particular module, let's say. What about if you connect it directly to a DC motor? Let's say a submersible water pump maybe, or a direct drive motor, or a motor in a vaccine refrigerator compressor. Here again, you have a curve that will intersect the IV curve. And wherever it intersects, it's the motor that tells the module to operate at this voltage and this current. And now finally, when we connect it to our electronic devices, let's say our inverters with maximum power tracking circuitry, it's that circuitry in the inverter that tells the module where to operate. So I draw a curve of constant power, which I will show later in different contexts, but that shows me constant power. And wherever that touches the knee, that gives me the point of maximum power of that curve, and that electronics tells the module to operate at that voltage and that current. So once again, though, it's the electronics of the load that tells the module where to operate. And finally, we can define something called the fill factor, which basically is, it's really just a measure of goodness. It's how square the curve is. You can't actually get a fill factor of 1. In fact, a really good cell module might have a fill factor of like 0.8, 0.78, 0.79. 0.8 would be super high. But it's a question really of how close can I get that max power to some sort of ideal idea that would use all the voltage and all the current that I get out. But that's just another way of thinking of the IV curve. So now I'm going to define this thing called the equivalent circuit of a solar cell. I don't know how many of you are familiar with this, but I'm going to jump right in. And I'm going to build it up slowly. So we begin with what's called a current source. For those familiar with electronics, that's this symbol. And a current source means it's a device that's shown on the graph here that delivers constant current no matter what its voltage environment is. That's the idea of a current source, okay? It's a special kind of idea. Well, in our case, we have sunlight jumping into a cell, knocking electrons loose, creating current, okay? That's the current source element. So we draw it like this. The physics is the actual photons coming in, but that's the element. Now, I keep going, and I'm going to introduce an internal diode. It's like I didn't actually take a diode and stick it inside of a cell. In fact, it turns out that the PN junction of a solar cell is a diode. So the solar cell is a diode already. It's got one built in. It's just that we take a diode, we scrape off the paint, and now we have a current source connected to it. But the idea is that we have an internal diode. And so you take this constant current device that I have, and you connect it in parallel with a diode, and you end up with a curve shape like this. Now we're going to define this curve shape in the lecture. I'm going to get into this in great detail. But now you introduce another element. It's a bit of shunt resistance, internal shunt resistance. Now, are we doing this on purpose? No, we don't want this. In fact, manufacturers try to limit this. But what might this be? Shunt resistance might be caused by internal microcracks. Maybe this is where recombination would occur. This is part of the idea where holes and electrons that are created will recombine. In other words, the electrons will be shunted within the cell because maybe holes and electrons recombine. Or maybe they find those grain boundaries in polycrystalline silicon. There's a shunt resistance. Manufacturers want this to be very high. They don't want to allow a lot of shunting, okay? But it exists. The effect on a curve of a cell or a module would be this kind of effect over here. This is what it would look like. At higher voltages, you'd have more shunting current, so less resulting current. The higher the voltage, the more current would shunt through the cell, and you'd have this drop in your curve shape. The final element to put in here is series resistance. Series resistance. What's the idea here? This would be, for example, the fact that silicon isn't a perfect conductor. It's got some resistance in itself, so it's there. Maybe the grid lines on the front are too thin or have some breaks. Maybe the connection to the interconnect wires between cells is not done well, so you have a little resistance there. Or in our arrays, maybe you're using wires that are too small. But the idea is that you can have some series resistance actually built into the cell itself. And the result there would look like this. It would bring in the slope of the curve on this side if you had series resistance. So now notice what I've got here. I've got a photo-generated current coming out from photons. I've got an internal diode current that's stripping some away. And the result that gets past these guys is the photocurrent, the PV, the IPV. This is the current that we measure coming out of the cell, okay? So there's the equivalent circuit of a solar cell. So now I'm going to jump into quantum physics, okay? Dykes, okay. But by the way, I love this stuff. This was my major. You know, I kind of think this stuff is cool, so pardon me. But don't worry, because I take all my inspiration. Remember, Einstein did most of his work when he was in his early 20s, although I don't get most of my inspiration from that Einstein. I get it mostly from this one, right? So we're going to go on from there. So here's a conceptual exercise, right? We're going to stay on this for just a moment, just to get the concept of how quantum stuff is so weird, okay? So I'm going to start animating this. Now, I'm going to begin. Look at A as one example. Think of it as being a ball that's confined in a space, and it's bouncing between the walls of that space, okay? Just an idea. So the ball can have continuously varying location and speed. We can know where it is, how fast it's moving. It can move a little bit faster, a little bit faster. We understand that intuitively, right? But when you get to the quantum level, where you're down to, you know, super small spaces, it turns out that matter starts behaving differently. For example, an electron has only discrete energy states and is confined to certain locations. That's different than the ball. The electron just can't increase its energy a bit. If it's in a confined space, like an orbital, like around an electron, if it's confined to the space, it has confined energy states. So look at B as an example and think of like flipping a rope, right? You've got it connected at one end, or think of it as a string on a guitar or whatever. You pluck it, and that it's confined at both ends, like this electron is going to be confined within an orbital space. And it has this mode of vibration. So it's got this one certain mode of energy. Think of that line as indicating a certain amount of energy. If you want to increase its energy, you can't just increase it a little bit. It's got to jump to C. It goes to a bimodal vibration. And if you want to increase its energy again, it can't just gradually go up. It's got to jump to D, where it's got a trimodal vibration pattern. So B, C, and D are indications. It's just a diagrammatic idea of the fact that the energy levels are discrete. They can't just continuously get bigger and bigger. They can only jump, boop, 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 which is really weird. It's fundamentally objectionable, right? It's like, how can that be? How come you can't go from one energy level to another? What about in between? Well, it turns out in the quantum world, you make the jump. There is no in between. And we're going to get to that further by not studying equations like that, but by looking at things physically. And I'm going to show you an example of how we know this is really true. This would be the spectrum of light that we get from the sun. So a whole bunch of elements are there, they're crashing into each other, and we get a full spread of visible. There's also ultraviolet, infrared radiation as well. This is what, you know, our eyeballs happen to capture. But if you were to heat up some hydrogen gas, okay, which is a simple element, it's just a proton and an electron, right? It's the simplest element you can get. So it's going to show us the quantum effects pretty simply. If you were to heat it up and look at the light that you get, this is what you get. Boop. That's it. Now, there are some wavelengths in the ultraviolet that we can't see and some in the infrared. This is what you get in the visible. But you only get these four. That's it. There are no in-betweens. That's reality. I mean, macroscopically, you heat up hydrogen, this is the colors you're going to see. It's real. But what's going on? How come there's only four? Well, that's because of the discrete energy levels of the orbitals of the electrons around that hydrogen nucleus. It's just the quantized energy levels that are available. Now I'm going to take this into a crystal state. I'm going to talk about silicon in crystal. I'm going to talk about energy bands in a crystal. What does that mean? What's an energy band? Well, vertically I draw energy. So we go up. If you're thinking up, we're thinking more and more energy. If I think about an isolated electron, just all by itself, just, you know, with electrons confined to their orbitals around that nucleus of that silicon atom, it turns out that the outermost electrons only have these two energy levels that they can emit light from, okay? Or that they can occupy. That's the energy levels that can be. It's either those two or that's it. But if I start to put a bunch of atoms together, bringing them together, imagine them coming together so that these orbitals start to overlap and interlock and intermesh with each other. And the physics starts getting mushed between all of them together. It turns out that what happens is those energy discrete states start becoming filled with billions and trillions of electrons, none of which can have exactly the same energy levels. They all have to be kind of next to each other. And it just turns out that they start to create bands of energy. A lower state of energy is called the valence band, and an upper state is called the conduction band. So what happens is that at rest, the valence bands are filled, all the energy levels that are possible are filled with electrons. And the conduction band is where they could be, but they're typically not there because silicon is not a good conductor. We're going to get to how they get there in a minute, but these are the energy bands that get created by putting a bunch of silicon atoms with orbitals next to each other. This is going to be a critical concept. And in between is this band gap. What does that mean? That means that you have energy levels there that cannot be occupied. You either are an electron in the valence band, or you get enough energy, boop, and you jump up to the conduction band. You can't just sit in the band gap. The difference here is, for example, if I was to show this picture for copper, the conduction band is dropped down and actually intersects with and is a part of the valence band. And so an electron has no gap. It can simply be around a copper atom, or whoop, it can just start wandering in the conduction band and be pushed along with some voltage and conduct current like we have in a copper wire. And that's great. That's what makes a conductor. And you can have materials that have a band gap that are super wider, 2, 3, 4 times wider than this. That would be like an insulator, where the energy needed to go from the bound valence band state for an electron to be able to become free is so great that it just never happens. No matter how much voltage you put on it, you can't break it free. And that is what we call an insulator. But semiconductors are great because they've got a band gap that it just turns out, the band gap energy matches the energy that we get from the sun. And that's the magic that we're going to take advantage of. And I'm going to show you that. So let's keep going with this idea of energy band gaps in crystalline silicon. On the left, I've drawn that picture, and I've filled it in with some black dots that represent electrons that are in that valence band. So remember, the valence band is the band of energy where the electrons are stuck. So think of these as being the electrons that are in those bonds that connect silicon to silicon, and they're just orbiting between the silicon atoms, and they're stuck, but they're holding it all together, okay? And conduction would be those free electrons, or those free holes, would be the free electrons that are able to move around, okay? So it turns out, just nature just gives us silicon with a band gap of 1.1 electron volts, 1.1 volts for an electron. It's just that way. And there's other materials that have other band gaps, but all semiconductor materials are going to be roughly around this level. So let's look at this. The drawing that I have on the right shows the spectrum of light that we get from the sun, with the horizontal axis being the photon energy, electron volts. It's not the usual way you see this. Usually it's with wavelength, but this is with energy. And then this is vertical is the amount. So this black line represents all the light, all the energy that we get from the sun. I show the visible right here. And here's the 1.1. So the idea is that if a photon of light has 1.1 electron volts or more, then it has enough energy to knock that electron loose. Let's look at that. The photon would come in, strike an electron that's bound, but now it would have enough energy to break it free, and that's that idea of that electron being ionized and able to move around. I'm showing it here in a different way. I showed it before in sort of a physical way. This is kind of in a band gap way, but it's the same idea. So the electron that got knocked loose is now in the conduction band, and this electron is the one that can move around. And what it left behind was a hole. And this hole is the hole that can wander around as well, right? So we've created the whole electron pair of charge carriers that can move around. And that's because, in this case, I looked at a photon of light that had at least 1.1 electron volts or more, which means everywhere from this region of the infrared into the red, orange, yellow, blue, violet colors, and here into the near ultraviolet. All of these guys have enough or more energy to knock that electron loose. That's how we get solar cells to work in the first place. Now, a critical thing I'm going to introduce here, just to mention, is This is one of the reasons why solar cells are not 100% efficient. This is one of the beginnings of the sources of the loss of efficiency. Because if, see, all of the light on the other side of the green line here, all of this light does not have enough energy. It has less than 1.1. And that's the all or nothing idea of quantum physics. If the light comes in and it doesn't have 1.1, it can't elevate the electron part way. It can't do it at all. And it just goes through. And so these low energy, long wavelength infrared lights, super long infrared light, can actually go right through a solar cell because they don't have enough energy to interact, and so they don't. So that's one of the sources, and we lose a lot of incoming light that we maybe could use, but we can't because it doesn't have enough energy, okay? So now, this is going to get a little mind-blowing, okay? I'm going to literally bend your mind here for a minute, so just hang on. If this gets a little confusing, don't worry. It's going to get clear, but hang on, okay? So I'm redrawing my picture here of intrinsic silicon. Now, I'm going to draw a line in the middle, and I'm going to label it the Fermi energy level, EF, whatever, just a term that I'm going to use. And think of this as kind of being the average measure of the states available for electrons. There's half as many states down here as there are up here. It's right in the middle of intrinsic silicon. Intrinsic silicon means it's undoped. It's just pure silicon, okay? This line is kind of like saying that the average American family has 2.2 kids, right? You don't have 0.2 kids, right? It's just a mathematical number. This guy, even though it's in the forbidden region here, it's the mathematical average point between the number of states that are available down here and the number of states that are available up here. Well, let's keep going. Let's remember about p-type silicon, right? How did this mess this up? Well, remember our p-type silicon is where we had the boron, which introduced those spots where electrons could go. Remember that? Okay. This is what it looks like in this diagram. This is another way of looking at it from a band gap diagram. These would be the boron sites right here. And you go, wait, dude, you just said that I can't put stuff in the forbidden zone. What's going on? Okay, that was for pure silicon. This is messed up silicon. This is silicon that's been doped. So I've mechanically put these atoms in place, and I've created these energy states in what was intrinsic silicon, but now I've made these states. And this is what happens. Remember, I can get electrons that are nearby those boron atoms to just boop, jump up and fill those vacancies that were created in those boron sites. And now these electrons get stuck there forever, right? And they left behind holes, which now can move around. That was the picture that I drew before, but now I'm just looking at it from a different point of view. But now what's happened is that I've created a whole bunch more possible states down at this low energy level thing. So my average energy level, my Fermi level, my average energy level has been lowered down, and I draw it way down here. I'm going to keep going. What about the N-type stuff that's at the front of the cell? Remember that? That was where I had phosphorus atoms that had those fifth electrons that pretty easily could just break away and move free. Well, now let's look at that from this point of view. What do you think that's going to look like? It's going to look like this. So now these are actually introducing those phosphorus sites. I've mechanically put them in place. I've messed up what was my pure intrinsic silicon, and I've put them in place here. And now these guys have energy levels that are so close to the conduction band. Remember, those electrons just could vibrate easily and break free, and that's exactly what they do. So these would be representing those electrons that break free from the phosphorus and can just start wandering around. And that's what the conduction band means. That's the band of energies that means I have enough energy to just be able to wander free. And it leaves behind those phosphorus sites that are permanently in place there. Those are those representation of those phosphorus atom sites as well. And what that does is that says, hey, I've introduced a whole bunch more possible states up here than down here, so I'm going to move my average line up. So it's up here now. Now, the reason that we're doing this is to do this. I'm building. See, I'm building all the way. Trust me, I'm building. These energy levels, the average energy level has to be the same if I put these guys together. If they're physically built together, which they are, when I make a cell, I build the N-type on top of the P-type. If they're physically together at equilibrium, at thermodynamic equilibrium, the average has to be average across both regions. And so what's happened is that the bands bend. This is kind of weird, okay? But the bands are drawn. I mean, physically there's no bending, but I'm just showing a drawing that shows that the bands are bent so that they can match up, so that the energy levels can be shown properly proportioned to each other. So now I'm going to take this, I'm building on this idea. I'm going to put this junction to work. Now I'm going to expose it to light for the first time, okay? So let's remember, this is the region where there's that electrostatic field. I'm kind of superimposing two ideas here, right? This is where the N-type, the phosphorus atoms, they lost their electrons, they went over here, fell in, got permanently stuck, and created a field of negative here, and where they left behind positive charges in the crystal structure here. So here's that electrostatic field in that junction. So this is the PN junction, this is the P-type, this is the N-type, okay? Now, let's put this in the sun. So I introduce a little electron down here in the valence band, just an electron around some silicon in the P-type, and I expose it to some sunlight. Remember, it goes all the way through the N-type. This is real thin. It actually, the light goes right on through. This is real thick. On a random basis, it hits this electron, and boop. If it's got enough energy, if it's got 1.1 electron volts or more worth of energy in that photon, it can ionize that electron. And that's what happens, right? There's my whole electron pair creation. So now it hasn't physically moved left or right, but now that electron now is free. It's in the conduction band. It's able to move around. And here's the hole that was left behind. And so now that electron hopefully wanders into that field and gets swept to the front. And notice what it did. It rolled down the hill. That's what people say. And I really don't like that because there's no hill. But the analogy would be like if there was a ball here and there was a hill in a gravitational field, the ball would be pulled in the gravitational field and would be moved forward down the hill by the gravitational field. And it would lose potential energy because it was falling down in the gravitational field. That's the analogy here. The electron falls into the electrostatic field and falls through the field, and in doing so, loses some of its potential energy because it's moved through the field. Basically, it's crashed into a bunch of objects there and moved through the electron, moved through the crystal structure. And don't forget that the hole can wander back the other way. So what I've done here is now I've taken the mechanical idea of that picture of the crystal structure with the electrons moving around, and I've combined it with this band gap picture as well. So now let's jump into the meat of why I wanted to run this whole seminar, which is how the curve gets its shape, okay? So let's put a bunch of this stuff together that we now have understood a bit better and make it into a flow of IV curve. But first, vive la résistance. We're going to talk about resistance for a moment because this is going to be needed for me to show you what I want to show you. So if we have a resistor, symbol for resistor, and using Ohm's law, R equals V over I. It's one of its many forms, right? So if I double the voltage, I have to double the current. If I half the voltage, I have to half the current, right? So, and these lines, like I showed you once before, these lines represent, in a sense, an IV curve for a resistor, right? It's a line. So in this case, for a low resistance, with just a little bit of voltage, I get a lot of current flow. If I increase my voltage a little bit more, I get a lot more current flow, right? That's true of a low resistor. Whereas with a high resistor, if I put in a lot of voltage, I still don't get much current. If I put in even more voltage, I still don't get much current, right? That's a curve for a high resistor, right? So I'm going to use this kind of variable line representing a resistor in this discussion. So now I'm going to put together three things that we've been seeing, two things plus one that we're going to start learning about. So the first perspective is this perspective of the electrostatic field, right, at the PN junction, right? Now I'm going to combine this idea. This was the idea of the electrostatic field. I have space, I have distance along the bottom here, but vertically now I'm going to draw on a graph of voltage or energy, right? That's where I'm going to reintroduce my bands, right? So down here, this is the top of the valence band, and this is the bottom of the conduction band. I don't show the whole band, I just show the top of one, the bottom of the next, right? And here I show my electron that's bound to silicon atoms, And up here, there would be electrons that would be free to move in the conduction band, okay? So I'm putting these guys together, right? And we remember that with silicon at room temperature, the band that has to be gapped is 1.1 volts. Okay, now I'm also going to bring along my equivalent circuit. I talked about it before, and I'm going to use it now to explain the third part, which is the shape of the IV curve. So we're going to generate this shape, but we're going to understand the physics of why it has the shape that it has, which is pretty cool. I don't think most people know about this. Most people can explain IV curves and they'll say, well, it's like a diode, but they don't go beyond that. So I'm going to step through a number of conditions of resistance. I'm going to start at 0 resistance. So what's that? That's like a short circuit, right? That's taking a module and taking the plus and minus wire and hooking them together. And you better not do that with a battery, but you can do it with a solar module because it's current limited. Pretty cool. So let's proceed to look at this. What does this mean? I take my solar cell, expose it to light. Light comes in with enough energy, ionizes that electron, creates a whole electron pair. The electron wanders, and once it gets into that field, it gets pushed by the field, gets separated from its possible hole, gets pushed to the front of the cell and goes out, and the hole wanders to the back of the cell, right? We've talked about this phenomenon now, right? But now, let's look at the energy levels of where you started and where you ended up. And it turns out that under this case, under this situation of this load, that's what's going to be important. Remember I said that the solar cell is a passive device and its output depends on what it's connected to? That's where that idea is going to come in. And right now, it's connected to nothing. It's got no resistance. So the electron that got energized rose up in energy and then lost it all. So in this case, where I've got short circuit current, I've got no voltage gain. So on my IV curve graph that I'm drawing here, I draw it at 0 volts. Now, the current is the photo-generated current, right? This photo-generated current, the photons coming in, generating current, flowing out. That's the green line flowing here. So that's the amount. So I'm going to draw that at this level. That's the level of the photon-generated current. Let's say for a cell, I don't know, maybe 8 amps or whatever it might be, okay? So that gives me my first point on my IV curve. That gives me my short circuit current point. 0 volts. I have no net voltage gain from all the work that I did with that light, but I've got some current flow. It's weird to have current flow but no voltage, but that's what we've got. But let's keep going, because this is the critical part that most people don't know about, okay? And this graph is actually kind of accurate. It's this kind of shape. It's a distribution graph. This is a profile of the electron energies in the conduction band. Remember, this is the bottom of the conduction band, so this is all the conduction band over here. Think of this graph vertically being going up in energy, like we always are, but horizontally being the number of electrons. So there's very few at this low energy level, most of them mid-band, and very few with lots of energy, which is true, right? There's always only a few that have the highest energies. And in this case, if I draw a line across from the threshold level of this band, let's say there are no electrons with enough energy to be able to actually flow the other way. There's no balls that are bouncing around here with enough energy to roll up the hill. None. So all the current that flows is the photon current, and that's what I show here. I'm going to keep going, and you're going to understand why this is important. So now, let's introduce a little bit of resistance. Again, I'm changing what the module or the cell is connected to. A little bit of resistance here, okay? So here's my line of little bit of resistance. So what's happening? I'm going to have electrons now be able to flow out of the cell through the resistance. Now remember what resistance means, right? Resistance. So the light comes in, knocks the electron loose, it flows through the field, the electron goes to the front, the holes wander to the back. But now what's happened? Because there is some resistance, right? It backs up some of the electrons. That's what resistance is, right? Think of, resistance of people walking down a hallway. They don't all get to go as quickly as they did when it was a short circuit. So there's a bit of building up of electrons here. Light comes in, knocks electrons loose. Not all of them get out. They build up. They gradually leak out. So now if I was to look at the two energy levels of where I started and where I ended, it turns out that these electrons here going out of the cell are coming from an environment where they haven't lost all of their voltage. They're piled together here. They still got, energy left in order to leave this region. So there is a bit of a voltage difference now because of this piling up of holes and electrons. And if I show that distance, that difference in E, in voltage, is shown as a voltage value. So that determines the voltage that I'm operating at based on this resistance. So I read up. At this voltage, I intersect my resistance curve. The idea is that I've got photons, I've got light current being generated, right? That's always going to be the same. Same amount of light coming in, same amount of photons coming in. But now the baseline has been raised a little bit. So now I've got a little bit of number of electrons that have enough energy to flow the other way. And this is called the diode current, ID. I diode. That's this guy. That's the internal diode effect in the solar cell. This is the internal diode. It's a PN junction. And so now I've got enough. I've got these little guys up here. I've got this amount right up here at the tip. There's enough to give me some that have enough energy to go the other way. And these are the two opposing currents that occur inside of a solar cell. And the net result that comes out is the photo-generated current minus the diode current, right? The photo-generated current minus the diode current is the net resulting PV current that comes out. Here's my voltage point. This would have been my photo-generated current level. But because I'm losing a little bit, I actually go down a little bit. Did you see that? Now, the trouble of drawing it here is that it's small. We normally draw these curves as being flat because we go, oh, the curve's flat, and then it drops off. Well, it's actually declining along the way, but only a little bit. But that circle went down because of this amount of the diode current that's starting to leak backwards. So now my next point on my curve, according to this voltage, is down a little bit. Let's keep going. Let's make the resistance bigger. Okay, so there's my line of bigger resistance. See, apply voltage. Now, instead of the current being up here, the current's there. Oh, I got more resistance. Same thing. Light comes in, knocks the electron loose, flows to the front, the holes wander to the back. But now I've got more resistance. So I've got more building up of charge and more building up of holes. I've got more building up of electrons here. I've got a retention of more of the voltage that I started with at the end. These guys haven't lost it all. They're like crowded. Think of a bunch of people crowded around a door, ready to go out. They've still got energy left to give. And so now that distance is shown up as more voltage that remains. And if I read up, it's going to hit my resistance curve right here. Remember, it's operating this curve. So it's got to be on the mutual curve of the IV curve and the resistance curve. So now the concept is I have that same photocurrent going forward, but now, because I've raised up my baseline, I have more high energy electrons with enough energy to flow the other way. So my ID becomes bigger. My reverse current is becoming bigger. So now, at this voltage point, instead of having this much current, I now drop it down that much, because the loss there is that internal diode current going the other way. So now my current is a bit lower, even though my voltage is higher. Let's keep going one more step. Same idea, same idea, same idea. Much bigger resistor. Light comes in, does the same idea. All the stuff is moving, moves to the front, moves to the back. And now I've got more piling up, right? Same concept. So now the difference that I'm building up between my voltages is even further out. So I've got even more voltage remaining that I can use. However, I still have the same amount of photo-generated current going forward, but now I've got quite a bit more electrons with enough energy now that they can actually flow the other way up against that hill. So my diode current subtraction is greater. So what happens is my photo-generated current, which is my potential possibility here, gets reduced by an even greater diode current there, and it drops down to that point. So you can see my shape, right? And now let's finish. Let's get to open circuit. How can we have open circuit? How can you have photons coming in and nothing coming out? How come the cell doesn't just blow up, right? What's going on? Well, what's going on with open circuit condition? Well, the load I'm connected to is an open load, right? There's no connection. That's my situation. So what's going to go on here? Light comes in, knocks my electrons loose, everything keeps moving. I separate my charges, and now what's happened? The electrons that were generated by the light have nowhere to go. I get a real buildup of electrons. So now I have a big gap between the voltage point where they started and the voltage where they're at right now, the voltage potential they have. I have my maximum voltage potential reading here. But let's think about the currents. I still have the same photo-generated current because it's the same amount of light coming in. But now, because my threshold level has been raised so high, the amount of electrons with enough energy to flow backwards is equal to the photocurrent. So now the diode current is equal to the photocurrent. Basically what's happening is that there's a circulation of current within the cell. Light's coming in, knocking electrons loose, and they're just circulating. No. Doesn't blow up, but nothing comes out. So the net current level, if these two are equal, the net current level is 0, right? The current flowing here is equal to the current flowing down the diode, and all the current is circulating here within the solar cell itself. So now, all that photo-generated current that I started with here, the green, all that current is lost. And I'm at a point where I have voltage, I can measure voltage here, but I've got no net current flowing out. And that gives me my IV curve. That's how it's shaped like that. And the reason that it's not linear is because this distribution curve, based on physics, is not linear. It has to do with the quantum calculation of the number of states and all that kind of crazy stuff. So that's where the curve gets its shape. So now, what I'm going to talk about is some environmental effects that we all know. Modules get hot in the sun, they lose voltage, yada, yada. How come? Okay, that's what we're going to look at here. And now we're going to be able to answer it from a physics point of view correctly. Now let's start looking at some stuff that we think is familiar. So IV curves are affected by their environment. One of those effects is the irradiance, or the amount of sunlight shining on the cell or the module or the array. And we show that typically this way. With less light shining, the IV curve has less height. With less light, we have less current. Okay? That's something that we should all know. And because the output of the module is affected by light, the industry has come up with a standard that's 1,000 watts per square meter of irradiance in order to measure the modules. In real life, it'll probably get less than that or more, but for a manufacturer to measure its modules, we need a standard around the world, and we've settled on this. And it's really weird because the 1,000 isn't arbitrary. If you measure, like at the equator, at sea level, under a certain defined clarity of sky, at noon, you get like 1,002 or something like that. It's crazy. So it was rounded to 1,000. It's actually measured. Out in space, it's like 1,350. But by the time it goes through the atmosphere, it gets down to 1,000. It's really pretty crazy that it's actually 1,000. Okay, so that's the standard. But whenever we draw these curves, there's always this change. And in fact, it drives me crazy when we have curves drawn and they all come to the same point. They don't. But okay, brilliant people, why does the voltage change and why doesn't it go down like light? If I get half as much light, how come I don't get half as much voltage? How come? Well, now we're going to be able to understand this. So let's take a look. So remember the whole situation we've got. We've got photo-generated current. So that's electrons that are now free to move in the conduction band, and they can flow. And we're talking about open circuit voltage here. Remember, open circuit voltage? That's where there's enough, well, there's nowhere to go. So the buildup of electrons is so much that this population of high enough energy electrons can flow backwards through the diode, and the two currents equal each other. Okay? So this condition results in zero current, right? zero current, maximum voltage. VOC occurs when the diode current going backwards equals the photocurrent going forward, right? And that creates and defines what we call the VOC at that point. Let's say under 1,000 watts of light. Now, let's reduce the amount of light. So let's look at the red curve, right? So what's going on? We have less photocurrent in this case. Everything before, I always kept the photocurrent the same. But now I'm changing the amount of photocurrent. I'm reducing it a lot. So if I have less electrons flowing this way, I'm going to need less electrons flowing back in order to make the total zero, right? So if my photocurrent is smaller, so then the reverse current can be smaller to result in the two currents being equal, right? So the piling up of electrons and the resulting elevation of this final voltage can be less in order for the condition to be that I get enough electrons flowing backwards. Now watch what happens. So basically, my elevation level can be lower. I can be at a lower voltage state with less electrons piled up so that I have enough electrons with enough energy that flow the other way, and these two become equal. So if my final voltage elevation needed to be less, the difference between where I started and where I ended up is smaller. And so that's why the voltage goes down. The buildup of current that you now understand that goes on inside can be less so that the internal current is zero. And if that buildup is less, it means that the resulting difference between the two, where I started and where I end, is less. That's what results in voltage going down. Let's keep looking at stuff here. What's the effective temperature? This is pretty straightforward, right? Okay, so now we know that as a module or a cell heats up, we lose voltage as the cell gets hotter. And because of that, the temperature of the cell is important. And we've all internationally agreed on a standard of 25 degrees centigrade, 77 degrees Fahrenheit. And that could have been anything. It could be 30, it could be 0, whatever. We chose 25, as most things are defined at 25. A lot are defined in Europe at 20, but just choosing it because that's kind of room temperature. So we're going to run machinery and stuff. Why not measure stuff at room temperature? That's all. But it's been established as that temperature. But when you take a module and put it out in the sun, it's going to get hot and it's going to lose voltage. Why? Why does it lose the voltage? How come this happens? Okay, so now let's keep going. Again, we're going to look at it from this point of view. Now, this would be our standard picture, right? Remember, this is, let's say, 1.1 electron volt difference between being a bound electron and being a conduction electron. And the difference between, and again, I'm talking about open circuit voltage now, right? So if I knock an electron loose, it rolls down the hill, they're piled up here. The difference between where I started and where I end is the voltage potential that I have available to you. That gives me my VOC. But now, what if I get hot? Okay? Now, consider this. The whole cell, let's say a single solar cell, is getting hot. All the electrons are bouncing around. They're starting to move faster. The silicon atoms are vibrating. The electrons are moving around more with more energy. They've got more kinetic thermal energy. Everything's got more energy to begin with. So it turns out that the baseline energy level is higher. The place where I start from is at a higher energy level. I don't need as much energy to become free because I'm already agitated more than I was before. You know, I'm a bound electron, but I'm kind of jiggling and I'm ready to go. And you don't need to push me as hard in order to break me free because I've already got more energy because of the thermal effect. So I've shrunk my band a little bit. But what does that mean? That means that when light comes in and knocks an electron loose from here up to here, it gained less energy. So it has less energy to give back. So that's why when the cells get hot, you have less voltage overall. Because remember, the voltage was the difference of what you started with and what you ended up with. And if you started at a higher level, you didn't have to rise as far, so you don't have as far to drop down. You don't have as much to give back. The cells themselves have less voltage. The electrons have less voltage to give back because they got less to begin with. And that's why solar cells lose voltage. So the VOC is smaller. It's because their internal voltage, their internal energy level is higher to begin with. They gain less from their light, so they have less to give back. Now, I'm going to finish up with one more talk, and this is going to start talking about different colors of light and different energies. And this is pretty cool, because this has to do with tandem solar cells and stuff like that. What's the effect of a spectrum? We don't think about this much because we can't control this. We can measure the light level, we can measure the temperature, but nobody measures the spectrum, okay? But solar cell manufacturers do, and they have to, for exactly what I'm going to tell you about now. So this gray curve right here, if you can see this, this gray curve is the curve that's called air mass 0. It's the curve of the distribution of light that we get from the sun. Our particular sun, other suns maybe with different materials would be different, but roughly it's this, right? So this is the wavelength, and this happens to show the visible region, but there's ultraviolet here, and there's lots of infrared over here that we get from the sun. Now, this curve represents what's out in space, air mass 0, outside of any air mass of the atmosphere. Once it goes through the atmosphere and gets filtered by aerosols and moisture and stuff like that, it drops down a little bit. It's got some gaps here where it's absorbed by water, and you get this distribution of light coming onto our solar cells on the Earth. Manufacturers have to simulate the light that they shine on their modules in order to measure their output, right? They better get that light right. So it has been established, just like 25 degrees and 1,000 watts. The spectrum of light, the amount of blue, greens, yellows, orange, and reds, has been specified into a distribution curve that is based on going through the air at 1.5 thicknesses, 1.5 atmospheres of thickness. The idea is that at noon, the sun shining straight down on you goes through basically 1 thickness of atmosphere. That would be air mass 1 mass of typical thickness. I don't know, 30, 40 miles of atmosphere. But in the morning, the sun is rising, it's going through more, right? Because it's coming at an angle. And then at night, or in the afternoon, it's going through more atmosphere because it's going at an angle. So early on, the industry established this distance and this angle where the module surface was tilted at 37 degrees and the sun angle was at 48 degrees, which basically defined going through 1.5 thicknesses of atmosphere. And that was chosen to be kind of a average, right? You can choose anything, so let's choose something that's kind of reasonable and gets us going. And by going through 1.5 atmospheres, you can define the exact profile of light that your solar simulator had better try to simulate. So that's the definition of air mass 1.5. And the G stands for global, as opposed to direct or diffuse. Where direct would be from the circle of the sun, and diffuse would be from the blue of the sky. Global is all of that added together. So going through 1.5 thicknesses of atmosphere, global, catching it all together. That's what defines it. So it's kind of going backwards. It's defining the spectrum based on the thickness of atmosphere that it's going through. But let's take this further. Let's look at how silicon responds to light. So this is critical to understanding, the blues and greens coming in and that idea of excess energy and stuff. So we're going to talk about this now. So this graph is the graph of what's called the spectral response of silicon. And you can look that up. Look up spectral response. And you can get different spectral responses for different stuff, like copper-indium diselenide, or gallium arsenide, or amorphous silicon. All these different cells have different spectral responses. Think of it being like the response of your eyeball, right, to light. This spectrum over here basically shows you where our eyeball responds to light. This graph shows you where silicon responds to light. But notice, it starts here, just begins here, at roughly 1,200 nanometers of wavelength. That corresponds to 1.1 volts of light, of energy in that light. And as we get shorter wavelengths, we get higher frequencies, more energy. So the response of the cell rises up to a peak, but then it starts to drop off. And notice that here in the near infrared, we get a high response. And down here in the violet, we get almost half as much. Why is that? Why isn't light coming in? Well, this is measuring amps out versus watts of energy in, not the number of photons in, but the energy that those photons bring. And the point is here, these guys are bringing in just roughly 1.1 electron volts. All of that wattage that's in that little photon is being used. Whereas these guys, I'm going to talk about this more, all of these guys have more than 1.1 electron volts worth of energy. They have that excess that gets lost. And so if I measure the amount of current out compared to the amount of energy that it brought in, this violet light knocks electrons loose, but I'm not able to use all the energy that it brought because some of it gets lost as heat. So the energy that I get out of with electrons from that light is half the energy that I get from red light. I'm going to keep going and show you that in a different way right here. So all light is not equal. And this is a little bit of physics to finish everything off. If I look at a photon of, let's say, violet or ultraviolet light, it might look like that. If I look at a photon of red, or actually think of the red going into infrared, we can't see it, but think of this as being infrared light. It looks like this. And the two wavelengths are not the same, right? So the red photon has double the wavelength of violet, right? Think of this as infrared and ultraviolet. So it's got double the wavelength. And referring to some physics, turns out that the frequency of light times the wavelength of the light is always equal to the speed of light. It's like, the distance that you go in one cycle times the number of cycles gives you the speed that you go at light. And I can rewrite this so that frequency is equal to c over lambda. The point here is that the frequency and the wavelength are inversely related. If I increase my wavelength, I decrease my frequency. If I decrease my wavelength, I increase my frequency, okay? Now, so the red photon has half the frequency of the violet, right? And now some more physics turns out from our friend Max Planck that the energy of a photon is equal to h times the frequency, h times nu. H is just a number, it's just a constant. So the point is that the energy is proportional to the frequency. Higher frequency light, more energy in that light, in that photon. Lower frequency, lower energy. So that's why we think of ultraviolet, high frequency light, being very energetic. It can go into your skin, cause cancer, stuff like that. So if the red photon has half the frequency, the red photon has half the energy of the violet. So photon to photon, they don't carry the same amount of energy. So it turns out that you need double the number of red photons to deliver the same irradiance, the same watts, as you would from the number of violet photons. And let's put this into practice. A solar simulator in one part of the world that's delivering 1,000 watts, doing its job, but of mostly red light, would have double the photons and therefore double the current of a simulator that delivered 1,000 watts, but of violet light. So you can have two simulators that are calibrated at 1,000 watts. Oh, okay, they're good, 1,000 watts, that's what we're supposed to do. But if it's mostly red and mostly violet, they will produce different results. And you can't have that. You've got to have simulators that produce the same result if you take a module from one simulator to another. So we got to get this right. So solar simulator manufacturers spend a lot of time filtering their light so that they can match that spectrum of the air mass 1.5 pretty carefully. So that if you take a module from one simulator with one output and you put it in another simulator somewhere else, you get the same output. They have to be concerned about that. We don't do that in our daily lives, but that's why you need all three conditions to make your standard test condition, your STC. It's always listed here. STC, you get your output numbers. What are they based on? 1,000 watts per square meter, 25 degrees C cell temperature, and air mass 1.5. That's why that guy's there, because the manufacturer that made this spec had to do it by obeying the light balancing of air mass 1.5 so that you can compare apples to apples. So we put them all together, and this is what fully defines STC conditions, including all these conditions which we now understand we have to know because of the physics underneath. So all I want to do now is finish on everybody's favorite topic, which is a bit of shading. So I'm going to get to this. I've covered the main points that I wanted to, which is the key physics inside of the cell and how come the cell works. But I want to finish putting it together just to finish up the whole talk. So each solar cell only contributes about 1/2 volt. So we put them together in series. Remember, we did this before. So I'm going to draw my curves now based on connecting solar cells in series. So when I connect things in series, I add them voltage-wise, right? At a certain current, add the voltage. At a certain current, add the voltage. That's what it means to connect things in series. The current has to be the same. So if I add another cell together, at this current level, I add the voltage. At this current level, I add the voltage. And that's how I create a curve that is the sum of multiple cells connected together in series, right? At every current level, I add the voltage across. That's how I draw the curve. Don't look up from voltage, look across from current. And at the current level, add voltage, 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 and you end up with the result. It's going to be important because that's how it's going to affect the curve shape. So now I'm going to create a whole module. I start with one cell, one curve. I add another cell, in series. Another cell, add another cell in series, right? If I have 20 cells in series, I have a group of 20. Push my curve out. Another group of 20 and another group of 20 could make a module with 60 cells. And that ends up with the voltage curve of the module, which is always made up of a bunch of cell curves, okay? That's how we get the module curve. So if the open circuit voltage of one cell was 0.66, after 60, the open circuit voltage of the module would be 40. If the max power voltage was 50.53, the max power voltage of the entire module would be out around 32, let's say. Okay? And one interesting point here, I can create an inverter IV curve. Really, I call it an IV envelope, right? And I can do that based on the parameters of a typical inverter. I can have a minimum voltage operating for the inverter and a maximum voltage. This gives me my operational window that the inverter is designed to work in. And it will have, let's say, a minimum max power tracking point and a maximum max power tracking point. And then I can connect these with an envelope curve that's defined by the power, the maximum power of the inverter, divided by the minimum max power voltage, and the power divided by the max power voltage. And in between, I'd have a curve of constant power linking them. And so the blue curve creates an envelope in which the inverter can operate, right? All those voltage current points. So it's not like the IV curve that was a select series of IV points that made a line. It's a region. It's an envelope. Anywhere under this blue envelope, the inverter can operate. And so this leads me to matching the number of modules I put in series with my inverter. If I can get my array curve to somehow fit within the envelope of the inverter, it'll work, okay? But now, let's introduce some shading and see what the heck's going on there. And I call it the dolphin nose because it looks like a dolphin nose to me, I think. Okay, so this is introducing something different that we haven't talked about yet. We've all been focused on the front here, which is the region of power generation with a positive current and a positive voltage and a positive power, okay? But what about back here? There is a region of power dissipation where I have positive currents, but they're operating at negative voltages, and that results in negative power. In other words, power being taken away from the circuit instead of being generated. And I can go back far enough in my solar cell so that my IV curve actually explodes on me. And this is dangerous. This is the reverse breakdown point of a solar cell. This is where basically a diode would break down. And this is bad. It can actually catch fire, can explode, it can do all kinds of bad things. Typically for a cell, it might be back here around 15 or 18 volts. It's not usually measured by manufacturers, but it can be determined. But it's way back here at around 15 volts. we don't want to let any cells that are shaded operate there. That's the key point. So remember, we're talking about cells in series and how we add voltage-wise, looking at different current levels. Now I'm going to shade a cell. So I'm going to introduce some shading onto one of my cells. And it's going to end up looking like this, right? There's the curve that's lowered down, lower light level on the cell. So the curve goes down. And there's the reverse part. It's going all the way back. And then way back here is breakdown. So if I was to connect these, if I'm adding them together, let's look at this new point, the short circuit point of my shaded cell. The shaded cell can add voltage at these low current levels. At this level, it can add voltage. At this low level, it can add voltage. But finally, I get to a point where it adds no voltage. And that gives me my final point here. And the shaded cell can drag back all the other cells to create a new short circuit point that's lower than my original one, all the way back here. Why is that? Let's look at that point. At that level, the good cells, at that current level, they can add voltage, which would normally put my point way out here. But now, my shaded cell, being forced to operate at that new current level, will operate, but at a negative voltage. No, thank you. So that negative voltage counters the other ones. And that point is chosen such that that negative voltage equals all the positive voltage of all the other cells connected together to it, so that the resulting effect is dragging them all back to zero. Pretty bad. But that's how it happens. So that's how a shaded cell can drag down the curve of a number of cells connected together. So now let's put that together. Let's take out what would be a good cell and put in a shaded cell. Remember, it can be operated back there. Now that's reverse breakdown voltage. I don't want to go back there. But if I do, this one cell can contribute voltage here, so it adds voltage here. But at this new short circuit level, it's not adding. And then it can continue operating in reverse all the way back to where it would break down. If we didn't protect the module and we allowed this cell to be operated at some high current level like this, it would operate here, it could break down, catch on fire, and we'd be in trouble. So we introduced bypass diodes. Yay! And this is what it means to introduce a bypass diode. I'm going to look at a group of 20. Let's say I have 20 cells protected by a bypass diode. It's connected in parallel with the group, not series, parallel. And this is what it looks like when I connect a diode in parallel with a group of cells. It does like this. Boop. I'm adding them together. So I have my 20 solar cells, and then I have my bypass diode, the effect of which is effectively limiting my reverse operation to just the voltage of that diode, which is about 0.7. So I'm limiting my voltage of the entire group to minus 0.7 and not more. It effectively makes the shape of my group of 20 and diode, the system of the 20 cells and the diode, now looks like the blue dotted line. That's the curve. So now let's put that into application. If we shade a cell in the group of 20, and it does, like we know, drag down, that one shaded cell can drag down the output of all the other 20 cells, it drags them down. But instead of continuing to drag them down in reverse, now at current levels above what that shaded cell could do, remember that new short circuit point, at current levels above that, it's limited to 0.7. The excess current above what the cells can produce is carried by the diode. It's called a bypass diode. The current bypasses the cells. This level of current from this level up bypasses the cells and only goes through the diode. And let's put that together and finish up by looking at the beneficial effect. So if I was to operate at this high current level, my shaded cell could be pushed to reverse breakdown, and that's very bad. But now, if I introduce diodes into my system, now I replace that group of 20 with an effective curve that looks like this. So there's my 20 with some shade, right? It's dragged down. But the effect is that the reverse voltage is only limited. So now the effect of these 20 and these 20 plus the shaded 20 creates a curve that, yes, it has this voltage at low levels, But at high levels above here, see, it's kind of hard to show, but there's only a drop of 0.7 right there. The voltage loss that I lose is limited to my 20 cells, unfortunately, plus then only 0.7 more. And I stay away from my reverse breakdown voltage points and prevent my modules from actually being damaged. So I just wanted to get that in as a final point about IV curves. So now when you connect it to an inverter, let's say, it looks at max power operation points, and where it would have normally operated there, now it operates here. And it can operate at this high current level without reverse breakdown, because remember, it's being protected by the bypass diode. Well, that brings us to the close of this course, and I want to thank you all for hanging in there, and I hope you really learned a lot. I just want to remind you that there is this $50 discount code for all people attending SEI to take any of our current online 6-week courses that are starting in November, and that we are offering a deep discount on our OSHA safety courses that are available, plus the third one on battery safety, which is currently for free. And I invite you to check out all of our other on-demand courses that are always available. These are all found at solarenergy.org. Thank you very much.